Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route through wonder, calm, and the quiet corners of the universe. If you're listening right now, perhaps you've already slipped beneath the sheets, found your favourite pillow, and let the day begin to dissolve behind you. Or maybe you're still awake, mind gently buzzing with thoughts, wondering just how long it'll take before sleep arrives. Wherever you are in this moment, in a warm apartment, a quiet bedroom, a softly lit dorm, or perhaps curled up on a couch in the middle of a city that never really sleeps, I'm so glad you're here. Tonight we're going to drift together into something that almost everyone does, but few truly understand. We're going to explore what sleep does to your brain, not just why you need it, or how long is enough, but what actually happens in your brain once your eyes close and your thoughts begin to unravel into dreams. It's easy to think of sleep as just a break, a nightly time-out, something that hits the pause button on your waking life. But inside your skull, something else is going on entirely. Something astonishing. Something noisy in a way, and yet deeply purposeful. While your body rests, your brain becomes a theatre, a construction site, a janitor's closet, and a library all at once. And none of it is random. So before we tiptoe into that mysterious world, I'd love to know, where are you listening from tonight? And what time is it for you? Is it late, with the stars already out? Is it early, when the house is quiet and the world hasn't stirred yet? Or somewhere in between, maybe a sleepless afternoon, or a moment of stillness in the middle of a restless night? If you find this space soothing, if it brings even a little bit of calm to your day, or helps slow your thoughts as you prepare for rest, I'd be ever so grateful if you tapped the like button or even subscribed. It's a small gesture, but it helps this quiet corner of the internet reach others who might be searching for the same kind of peace. Now then, let's begin. Take a slow breath. Let your mind relax just a little. We're about to wander into something that happens every night, and yet feels a little like magic every time. It starts in the same way for nearly everyone. Your eyelids begin to grow heavy. Thoughts start to lose their edges, and before long, you're no longer quite here. You're not fully gone either, at least not yet. In that strange in-between state, your brain is already making decisions on your behalf. Chemicals are shifting, electrical patterns are changing, and your consciousness is slowly being moved aside. You don't tell your brain to sleep. It takes over, like a gentle but firm usher guiding you to the back of the theatre. Most people think of falling asleep as a kind of shutdown, like turning off a machine. But in reality, it's more like switching modes, from one state of processing to another. The brain doesn't power down. In fact, some parts of it become more active than they are when you're awake. It's not random activity, though. It's part of an intricate sequence your body has been rehearsing your entire life. Right now, researchers estimate we spend about 1/3 of our lives sleeping. That's more than 25 years if you live to 80. Imagine 25 years spent in a state that, for centuries, we didn't fully understand. And even today, with high-resolution scans and endless studies, much of sleep is still wrapped in mystery. But what we do know, what science has pieced together, is that sleep isn't just a break. It's a vital, non-negotiable process that transforms your brain every single night. The very moment you begin to drift off, your brain starts shifting gears. Waves of electrical activity slow down. Neurons begin firing in different patterns. Your breathing changes. So does your heart rate. The brain starts guiding you through a set of distinct stages: light sleep, deeper sleep, and eventually rapid eye movement, or REM. These stages aren't just labels. They represent entirely different states of consciousness, different types of processing, and different effects on your mental and emotional health. But before we even reach REM, there's something more subtle happening. As your brain slips into light sleep, it begins filtering out the outside world. Your senses are still technically functioning. You can still hear sounds, feel temperature, register your own position, but your brain is becoming less responsive to them. That's not by accident. Your brain is creating a buffer, gradually pulling you away from wakefulness and reducing your connection to stimuli that might otherwise jolt you back into the world. It's like lowering the volume on everything around you, one knob at a time. As you move deeper into sleep, the brain starts a new kind of operation. It's not passive, it's not quiet, even if your body is still. Inside your skull, billions of neurons are coordinating in waves. Large populations of cells begin firing together, then relaxing together. These waves, known as slow waves, define what's called deep sleep, the kind that leaves you feeling refreshed. It's in this state that your brain begins some of its most important maintenance work. One of the brain's key tasks during this time is cleaning. That's not a metaphor. Actual waste, molecular debris from the day's mental activities, begins to accumulate while you're awake. Proteins, byproducts of neural metabolism, fragments of thought and effort that, if left alone, could begin to interfere with normal brain function. During deep sleep, the brain engages something called the glymphatic system, a kind of neurological plumbing network that flushes out this waste. Think of it like a nightly rinse cycle for your brain cells. Cerebrospinal fluid is pumped through the brain, washing away excess proteins and toxins. This system is about 10 times more active during sleep than while awake. Without this nightly cleansing, harmful materials begin to build up, and over time may even contribute to neurodegenerative diseases like Alzheimer's. But waste removal isn't the only thing going on. Your brain is also editing. While you sleep, particularly during certain phases, it begins to sort through the vast amount of information you absorbed during the day. Some of that information gets stored, some of it gets tossed. This sorting process isn't just about memory, it's also about emotional regulation, learning, and even creativity. Imagine your brain as a vast newsroom, flooded with incoming data, memories, sensations, fragments of conversations, flashes of colours, moments of worry, snatches of song lyrics, the smell of coffee, the face of a stranger on the subway. Not everything makes the front page. Not everything even gets filed. But someone, somewhere in that mental newsroom is making decisions. What gets kept? What gets discarded? What gets moved to long-term storage? Sleep is when those decisions happen. The hippocampus, a small seahorse-shaped structure deep in your brain, plays a central role in this process. It's responsible for forming new memories and works in tandem with other regions to decide what sticks and what fades. During the night, the hippocampus replays patterns of neural activity from earlier in the day, like a rehearsal. These patterns are sent to the neocortex, where long-term memories are believed to be stored. This replay seems to help strengthen connections, reinforce learning, and allow new information to integrate into what you already know. It's part of why studying before sleep can actually improve retention. It's not just repetition, it's a collaborative biochemical editing session happening entirely behind the scenes. There's also something quietly remarkable about the way your emotional brain resets during sleep. When you're awake, particularly during moments of stress or excitement, your amygdala, a small almond-shaped part of the brain involved in emotion, is highly active. It helps you respond quickly, sometimes irrationally, to perceived threats or opportunities. But that activity, if sustained too long, can become exhausting. Sleep provides a kind of reset. During certain stages, particularly REM, emotional memories are revisited in a safe, low-stakes environment. It's like your brain is gently reprocessing feelings, examining them with just enough distance to take the sting out. This may be one reason why things often feel less overwhelming after a good night's rest. And that brings us into the more mysterious territory, the dream state. REM sleep is named for the rapid movement of the eyes beneath closed lids, but what's happening in the brain is far more intriguing than just twitching muscles. During REM, your brain activity looks remarkably similar to when you're awake. Certain regions, like the visual cortex and parts of the limbic system, become highly active. At the same time, the prefrontal cortex and the part responsible for logic and decision-making becomes less active. This unique combination creates a mental space where vivid, emotional, often illogical experiences unfold. Dreams. No one fully knows why we dream, but theories abound. Some believe dreams are a way for the brain to simulate scenarios, like mental rehearsals for real-life challenges. Others suggest they're a side effect of memory consolidation, a kind of narrative stitched together from the fragments being moved around. What's clear is that the dreaming brain isn't random. It's not noise. It's structured in a way that reflects deeper cognitive processes: memory, emotion, association, and creativity, all working together in the dark. Interestingly, not all parts of the brain sleep at once. While large-scale waves of activity shift across regions, some areas remain more alert than others. This uneven distribution of sleep may help explain phenomena like sleepwalking or even lucid dreaming, where parts of the mind become aware that dreaming is taking place. It also suggests that the sleeping brain is never truly disconnected from the world, only selectively tuned out. Even now, as you listen to this, your brain may be preparing for the next transition. Melatonin, the hormone that helps regulate your sleep cycle, begins to rise in darkness, nudging you toward rest. At the same time, body temperature slowly drops, heart rate eases, and blood pressure lowers. The brain is not reacting to these changes, it's orchestrating them. Sleep isn't just a passive response, it's an active process, designed, refined, and enforced by a web of interconnected systems that stretch from your brainstem to your hypothalamus and beyond. And yet, for all this complexity, sleep still manages to feel simple. You close your eyes, you wait, you're gone. But under that surface, the brain is performing a nightly miracle. Cleaning, cataloguing, soothing, solving. It's not an escape from consciousness. It's an altered form of it where your mind, unburdened by the distractions of the day, can tend to its own quiet work. As your brain sinks further into the patterns of sleep, the rest of the world often seems to vanish. Not because it truly disappears, but because your awareness of it begins to dissolve bit by bit. It's not just that your eyes are closed, it's that your brain, intentionally and carefully, is deciding to stop paying attention. Sounds fade, light loses its meaning, time itself becomes slippery. But interestingly, this shutting out of the external world isn't something that happens only inside your skull. It's mirrored all around you, by almost every living thing on the planet. Most animals, humans included, sleep. It's not just a personal ritual, it's biological, it's environmental, it's universal. For billions of years, the rhythm of Earth's rotation has shaped the behavior of everything on it. Light and dark, day and night, warmth followed by stillness. Even the most distant corners of the animal kingdom obey these cues. There are jellyfish that pulse more slowly at night, plants that fold their leaves, bacteria that become less active in the absence of sunlight. On some level, the world knows how to rest. For humans, this nightly closing of the eyes is more than just a habit. It's a shift in how we relate to our surroundings. When the sun goes down and artificial light begins to take over, we ease into a different state of mind. The hustle of the day recedes. Decisions grow fewer, conversations quiet down. Our senses are no longer on high alert. The brain, receiving less input from the environment, begins to turn inward. Inside your head, certain regions take the lead in initiating sleep. The suprachiasmatic nucleus, a tiny bundle of neurons in the hypothalamus, acts like a conductor. It uses cues from light to coordinate your circadian rhythms, the internal clock that helps determine when you feel sleepy, when you feel alert, and when your body performs various essential tasks. This system is tightly regulated by hormones, most notably melatonin, which increases as evening approaches, sending signals throughout the brain and body that it's time to wind down. But these changes aren't happening in isolation. They're part of a broader planetary choreography. As the sun sinks below the horizon, everything adjusts. In urban areas, lights come on, people head indoors, and the pace of life slows just slightly. In more rural settings, Silence expands. Even in bustling cities, there's a gradual shift in mood. The energy of the day giving way to something softer. Screens flicker in dark rooms. Conversations move indoors. Streets grow quiet, one intersection at a time. These changes in the external world influence your brain more than you might think. Light, for example, remains one of the most powerful regulators of your sleep-wake cycle. The blue light emitted from screens and LED bulbs can suppress melatonin production, delaying sleep and altering the depth and quality of rest. It's not that the brain is confused by artificial light. It simply interprets it as a signal that day hasn't ended yet. Your internal systems trust light more than the clock. That's part of why traditional societies, those with limited exposure to artificial lighting, tend to sleep in patterns more closely aligned with the natural day. Studies have shown that people living without electric lights often fall asleep earlier, rise before sunrise, and experience more consistent sleep cycles. Their brains, less interrupted by the artificial signals of modern life, follow the cues of the world around them. The closing of eyes coincides more neatly with the closing of the sky. But what exactly is the purpose of this global pause? Why do we, along with so many other species, retreat from activity for a significant portion of every day? Evolutionarily speaking, it seems counterintuitive. Sleep leaves you vulnerable. It takes time away from hunting, foraging, reproducing, and defending yourself. And yet, the need for sleep has persisted across nearly every species we've studied. That suggests something important, that whatever sleep is doing, especially inside the brain, it's worth the risk. The benefits outweigh the vulnerabilities. Consider dolphins who've evolved a solution to this problem. They sleep with one hemisphere of the brain at a time. One half rests, while the other remains awake enough to surface for air and stay alert for predators. This form of unhemispheric sleep shows just how essential rest is to brain function. The dolphin doesn't give up sleep, it just finds a way to get it without losing awareness entirely. Birds, too, demonstrate remarkable sleep flexibility. Some species can nap mid-flight during long migrations. Others sleep with one eye open, quite literally, allowing part of the brain to stay vigilant while the rest recovers. These adaptations suggest that even partial sleep is better than none. The brain demands its downtime even in extreme circumstances. Back on land, in the quieter parts of the world, animals follow more familiar rhythms. Nocturnal creatures emerge as the sun sets, guided by their own circadian patterns. Diurnal ones, like us, find shelter, settle in, and prepare for rest. It's not uniform, it's not synchronized, but there is a rhythm, a quiet pulse across the planet. It's not hard to imagine it, a global wave of consciousness fading into sleep, one time zone at a time, as if the earth itself were blinking slowly. Inside your own home, this rhythm is reflected in routine. Maybe you turn off the main lights, switch to something dimmer. You brush your teeth, adjust the covers, check your phone one last time. These behaviors aren't arbitrary. They send signals to your brain, cues that it's time to disengage from stimulation and prepare for a different kind of awareness. Over time, these patterns become almost automatic, habits that help bridge the gap between waking and sleep. Once you lie down and close your eyes, the brain begins actively disengaging from the world. The thalamus, a sort of relay station that channels sensory input to the cortex, begins to filter. It reduces the flow of information from your senses to your conscious mind. Not completely. You can still be woken by a loud noise or a sudden movement, but enough to allow the slower waves of sleep to begin. This gatekeeping is crucial. Without it, the brain would be overwhelmed by every creak, breath, and flicker in the room. As this sensory curtain lowers, you may notice strange moments, fleeting images, fragments of thoughts that don't seem connected. These hypnagogic experiences which occur during the transition from wakefulness to sleep are a sign that your brain is shifting modes. It's no longer processing the external world in the same way. It's starting to create internally generated experiences, the early stages of dreaming, the first signs of detachment from the present. But even as your conscious awareness fades, the brain continues scanning. Not the outside world, but the internal one. Systems are checked, hormone levels are monitored, temperature is regulated, the brain is still very much in control, but its priorities have changed. It's no longer focusing on movement or decision-making or external threats. It's focused on repair, regulation, and memory. Throughout the night, as sleep deepens, the brain cycles through phases that shift every 90 minutes or so. Light sleep gives way to deep sleep. Then comes REM. Then the cycle begins again. This rhythm is consistent in healthy sleepers and forms the backbone of a restorative night. Disrupting this cycle, whether by light, noise, stress, or interruptions, can reduce the benefits of sleep, particularly for the brain. In many ways, sleep is the brain's way of stepping back from the noise. The thoughts, tasks, and emotional weight of the day are paused, not erased, not forgotten, but suspended, given time to settle. This settling process doesn't just feel good, it's necessary. Without it, the brain struggles to maintain balance, cognitive function declines, emotional regulation becomes harder, memory falters, even basic tasks begin to feel overwhelming. In people who are sleep deprived, this shows up quickly. Concentration weakens, reaction times slow. The prefrontal cortex, the part of the brain responsible for planning, judgment, and decision-making, becomes less efficient. Meanwhile, emotional centers like the amygdala become more reactive. It's a double effect. You think less clearly and feel more strongly. It's harder to process nuance, harder to stay calm, harder to remember what matters and what doesn't, and this is why the world closes its eyes. Not just to conserve energy, or to rest muscles, but to protect the brain from being worn thin by constant stimulation. Every system in the body benefits from sleep, but none more so than the mind. Sleep allows for recovery, recalibration, and restoration. It's not a break from life, it's a vital part of it. What's remarkable is that this process unfolds night after night, often without our awareness. We don't command it, we don't initiate it, we allow it. And it comes, if conditions are right, if the environment cooperates, if stress doesn't interrupt, it comes with a kind of quiet reliability, like a tide, like gravity. And while our conscious experience of sleep might feel blank, the brain is experiencing something rich, patterned, and meaningful. A process shared across species, across cultures, across centuries. A nightly return to something essential. A reminder that, for all our complexity, we are still biological creatures shaped by the turning of the earth, the fading of light, and the need to occasionally close our eyes and step back from the world. The moment sleep begins isn't the end of awareness, it's the beginning of a new kind, quieter, deeper, and built not on perception, but on restoration. And as your brain turns away from the outside world, it turns inward, beginning a journey through phases of activity designed to rebuild, protect, and prepare you for everything that will come next. As the outside world fades and the last fragments of conscious thought begin to dissolve, your brain initiates one of the most finely tuned processes known to biology. The shift from wakefulness into sleep isn't a sudden blackout. It's a transition, a carefully controlled descent through layers of neural activity. You might not feel it happening, but your brain knows the steps. And the moment you drift off, the very first true moment of sleep, marks the beginning of an entirely new state of operation. Even though it can feel like you're gone, like you've stopped paying attention, the brain doesn't power down. It switches over, from alertness to internal monitoring, from external input to internal processing. The regions that once lit up in response to light, sound, language, decision-making, and movement begin to quiet. But they don't go dark. They're still active, just differently so. Meanwhile, new areas begin to dominate. Sleep isn't just rest, it's organization, cleaning, synthesis, repair. The very first stage of sleep is often so subtle that many people don't realize they've entered it. You might think you're still awake. You may still hear things, still feel aware of your body, still be loosely connected to your environment. But something has changed. The electrical patterns in your brain have slowed. Your muscle activity has decreased. Eye movement has become gentle and drifting. This is the earliest phase of what's called non-REM sleep. Technically, it's stage 1. In this stage, your brain's alpha waves, those gentle waking rhythms, begin to fade, replaced by slower theta waves. These waves are less organized, more variable. Your thoughts begin to fragment. You might have strange, dreamlike flashes, images or sensations that appear briefly, without context or logic. This is the hypnagogic state, a kind of mental in-between. It's a place where your consciousness is still partially active, but your brain has begun the handoff to sleep. The thalamus, which acts as a gatekeeper between the outside world and your cortex, starts reducing the flow of sensory input. It's not a total shutdown. If someone calls your name or a loud sound occurs, you can still wake up. But the thalamus is lowering the volume on the world. It's preparing the brain to focus inward, to begin its nightly routines without interruption. One of the first systems to become more active during this early sleep phase is the parasympathetic nervous system. This is the branch of your autonomic nervous system responsible for rest and digestion, the opposite of fight or flight. Heart rate slows, breathing deepens, blood pressure drops, muscles relax further. The body is being told gently and consistently that it's safe to let go, that it's time to repair, not react. During this early transition, the brain also reduces production of certain wake-promoting neurotransmitters, chemicals like norepinephrine and serotonin, which are associated with alertness, gradually decline. In their place, other neurochemicals rise, ones associated with sedation, memory consolidation, and brain maintenance. One of these is GABA, an inhibitory neurotransmitter that plays a central role in helping neurons calm down. By dampening excitatory signals, GABA allows the brain to enter sleep more deeply, more completely. From stage 1, the brain flows naturally into stage 2 sleep. Here, brain activity slows even more, but interestingly, it doesn't go silent. In fact, some very specific and important events begin to take place. If you were to look at an EEG, a device that records electrical activity in the brain, you'd start to see short bursts of rapid activity called sleep spindles. These are quick, rhythmic pulses, like little sparks in the quiet. They're thought to be involved in memory consolidation and the protection of sleep itself. The more spindles you have, the more likely your brain is to resist being woken up by minor noise or disturbances. You'd also see something called K-complexes, large, slow waves that appear in response to stimuli. These are brief but dramatic changes in voltage, and they seem to help the brain assess whether a disturbance in the environment is worth waking up for. It's a kind of passive monitoring. Even in sleep, the brain remains aware enough to scan for threats, but with a bias towards staying asleep unless necessary. At this point in the night, your muscles are fully relaxed, your breathing becomes more rhythmic, your eye movements stop. This is when your brain and body are finally sinking into a full sleep state. You're not dreaming yet, but you're no longer thinking either. You're in the part of the night where your brain starts laying the groundwork for everything that will follow. These early stages of non-REM sleep serve a foundational purpose. They allow the body to unwind physically, and the brain to create the right conditions for deep sleep. It's in these next stages, particularly stage 3, that the brain begins the heavy lifting of neurological maintenance. Stage 3, often referred to as deep sleep or slow wave sleep, is defined by the appearance of delta waves, the slowest and largest brain waves observed during sleep. These waves move at a frequency of less than 4 cycles per second. They are broad, synchronized pulses of electrical activity, and they signal that the brain is in a state of deep rest. This is the phase of sleep that is most physically restorative. It's when tissue growth and repair occurs. It's when the body produces growth hormone, which plays a role not just in development, but in muscle repair, immune function, and overall recovery. If you've ever felt profoundly refreshed after a long, uninterrupted night of sleep, it's because you spent ample time in this stage. But the brain is also deeply involved in its own maintenance during deep sleep. This is when the glymphatic system, the brain's waste-clearing network, becomes most active. Cerebrospinal fluid flows more freely through the brain's tissues, flushing out metabolic waste products that accumulate during wakefulness. Among these are beta amyloid and tau proteins, which when not cleared effectively have been linked to neurodegenerative conditions. Deep sleep isn't optional, it's protective, it's preventative, it's how the brain keeps itself clean and functional. What's also fascinating about deep sleep is how resistant it is to interruption. If someone tries to wake you during this stage, you might feel groggy, confused, or disoriented. That foggy feeling is called sleep inertia, and it reflects how deeply the brain had withdrawn from external processing. You were not just asleep, you were immersed in a different kind of consciousness. Despite its importance, deep sleep tends to occur more heavily in the first half of the night. Your brain prioritizes it early, as if front-loading the most critical repair work before easing into lighter, more cognitively focused phases later on. That includes REM sleep, the stage most associated with dreaming. But before REM can begin, the brain completes one or more full cycles through non-REM stages. These cycles usually last between 70 and 110 minutes, and they repeat, again and again, through the night, though not identically. Early cycles feature more deep sleep. Later ones lean more heavily into REM. The moment you drift off, then, sets in motion this entire sequence. It's not linear, it's not simple, but it's reliable. Unless you're sick, severely stressed, or dealing with a sleep disorder, your brain moves through these cycles with remarkable consistency, and it remembers. If you miss sleep one night, your brain will attempt to make up for it. It will prioritize deep sleep in the next cycle, often at the expense of lighter stages. If you're sleep deprived for longer, it may even attempt to compress and accelerate sleep processes, fitting in more deep or REM sleep into shorter windows. This sleep rebound effect shows just how essential these stages are. The brain doesn't give up on its nightly work, it delays it, then rushes to catch up. Even dreams, though often associated with REM, can occur in earlier stages. They're less vivid, less narrative, but they hint at the brain's continuous work behind the curtain, sorting, replaying, rebalancing. There's no single switch that turns dreams on or off. The brain is always generating activity. It's the quality and structure of that activity that changes. All of this starts in the very moment you drift off. That first shift in brain waves, that first breath that slows, that first flicker of disconnected thought. It's a quiet launch into one of the most complex choreographed biological events we undergo, one that repeats nearly every night of our lives. And it's not just repair, not just maintenance. As your brain eases into these rhythms, it's preparing for something even more elaborate. Emotional processing, memory sorting, neural growth, even creative insight, all of that is still ahead. But it starts with that single moment, the gentle slip from consciousness into something else. A handover of control from your waking self to something deeper, older, more automatic. A signal to the brain. The world can wait. It's time to begin the work of the night. Once sleep has taken hold and your body has surrendered to stillness, the brain begins the real work. This is when its night shift begins. Not a break from activity, but a change in priority. The parts of your brain that spend the day responding to your surroundings, making decisions, keeping you balanced and social and aware begin to slow. In their place, a different set of systems takes over. One's concerned with preservation, organization, and regulation. From the outside, you might appear peaceful, even motionless. But within your skull, it's a carefully managed operation running on a schedule your brain has kept since before you could speak. At this stage in the night, You've likely moved through the lighter phases of sleep and into deeper, more restorative patterns. Your body is doing less, movement is minimal, muscle tone is reduced, reflexes have quieted. You're not just disconnected from the external world, you're deep within the internal one. This is when the brain focuses most intensely on the tasks it can't easily perform while you're awake. The most well-known function during this time is memory consolidation. While you're awake, you're constantly taking in new information, conversations, visual scenes, facts, locations, emotions, decisions. But your brain doesn't store all of that immediately. It holds much of it temporarily in a kind of mental waiting room. Sleep is when your brain goes back through those experiences and decides what to keep, where to store it, and how to integrate it with what you already know. That work is distributed across multiple regions. The hippocampus, critical for forming new memories, replays sequences of neural activity from your day. These patterns are then communicated to the neocortex, where long-term memories are believed to be encoded. It's a bit like a rehearsal, practicing important experiences so they become more deeply embedded. And this isn't just about facts or names. Emotional memories, physical skills, and abstract associations all undergo this replay process. Sleep spindles, those bursts of brain activity that occur during stage 2 sleep, are believed to help transfer memories from the hippocampus to the cortex. The stronger and more frequent these spindles, the better the integration. In this way, sleep isn't passive at all. It's an active memory editing session. The brain sifts, replays, strengthens, or sometimes erases what it deems relevant. What you remember tomorrow is shaped not just by what you experienced today, but by how your brain handled it tonight. Beyond memory, this period is also a time for emotional calibration. During waking hours, your amygdala helps detect threats and assign emotional weight to experiences. It's one of the most reactive parts of your brain, scanning for danger, triggering fear, pushing you to act quickly. That's helpful when crossing a busy street, but taxing if left unchecked. During REM sleep especially, the brain reprocesses emotional experiences, often without triggering the same stress response. Studies show that REM can help reduce the emotional intensity of memories without erasing the memory itself. It's not forgetting, it's softening. Sleep lets your brain revisit what happened, the argument, the mistake, the surprising news, but with a gentler lens. When you wake up feeling more at peace with something that felt overwhelming yesterday, that's often sleep doing its job. This recalibration isn't just for one emotion, it's broad. Sleep affects mood regulation across the board. When people are sleep deprived, irritability rises, patience decreases, and emotional control suffers. The brain struggles to keep reactions proportional. Small setbacks feel larger, confidence wavers, optimism fades. But after a good night's sleep, those same events seem more manageable. The emotional brain has been rebalanced, like a thermostat reset to the right temperature. During the night shift, the brain also focuses on neuroplasticity, the ability of neural networks to change and adapt. This isn't just about learning facts, it's about forming new connections, rerouting around damage, building better habits, recovering from stress. Sleep supports the production of proteins and growth factors that promote synaptic remodeling. In simple terms, your brain is physically changing while you sleep. Neurons strengthen their connections, prune unnecessary ones, and adjust their signaling. It's a kind of invisible sculpting, delicate, silent, and ongoing. This process is especially pronounced in children and adolescents, whose brains are still developing rapidly. But it continues throughout life. Even in adulthood, the sleeping brain is capable of reshaping itself. It's one of the reasons sleep plays such an important role in rehabilitation after injury or trauma. Neural repair doesn't happen at random. It follows rhythms, and those rhythms depend on sleep. Another critical task the brain performs at night is metabolic regulation. While you sleep, energy use in the brain decreases in some areas and rises in others. The brain uses this period to manage glucose metabolism, regulate appetite hormones like leptin and ghrelin, and process insulin sensitivity. These aren't just physical tasks, they're deeply connected to brain health. Poor sleep disrupts these processes and increases the risk of metabolic disorders. Even a single night of fragmented sleep can impact your body's ability to manage blood sugar levels. It's not just about rest, it's about regulation. One of the most surprising discoveries in recent years is how deeply sleep affects the immune system. During sleep, the brain and body communicate closely to coordinate immune responses. Inflammatory markers decrease, antibody production increases, immune cells are redistributed to prepare for pathogens. Sleep doesn't just help you feel better when you're sick, it strengthens your body's ability to fight illness in the first place. Studies have shown that people who get adequate sleep after vaccination develop stronger and more lasting immunity. It's not a coincidence, it's cooperation between the nervous and immune systems, managed in large part by the brain during sleep. While this repair and regulation takes place, your brain continues to cycle between different stages of sleep. Deep sleep dominates the first part of the night. Later on, REM sleep becomes more prominent. These REM phases occur roughly every 90 minutes and grow longer with each cycle. By the early hours of the morning, you may spend 20 to 30 minutes at a time in REM. It's a different kind of mental activity, one that resembles waking thought but without the same boundaries. During REM, brain activity increases significantly in certain areas, especially those associated with emotion, memory, and imagery. The visual cortex lights up, so does the limbic system. But the prefrontal cortex, responsible for logic and self-monitoring, becomes quieter. That's one reason dreams often seem surreal or inconsistent. The usual editor has stepped away, and the brain is free to generate experiences without needing them to make perfect sense. But these dreams may not be meaningless. Research suggests they play a role in emotional processing, creativity, and problem solving. The brain makes unusual connections, it simulates scenarios, it works through unresolved concerns. People who are woken during REM sleep often report dreams that are emotionally intense, symbolically rich, or strangely insightful. The content may not always be logical, but the underlying activity appears purposeful. Interestingly, even the act of dreaming may serve a function. Some scientists believe dreams help the brain simulate social situations, threats, or unfamiliar environments, essentially rehearsing challenges while you're safe and unaware. Others suggest that dreams are a kind of emotional data compression, helping the brain store complex feelings in a more efficient way. The exact purpose remains debated, but the timing and structure of REM sleep indicate it's far from random. Meanwhile, outside of dreams, the brain is still tracking internal time. It doesn't lose track of the night. The suprachiasmatic nucleus continues to monitor circadian rhythms, even without external light cues. Hormone levels adjust as morning approaches. Cortisol, the hormone that helps promote wakefulness, begins to rise. Melatonin decreases. Body temperature starts to climb slightly. Heart rate begins to increase. The brain is preparing to transition again, not abruptly but gradually. Just as it guided you into sleep, it will guide you back out. The final hours of the night may involve lighter sleep, more dreaming, and brief moments of semi-consciousness. Periods you may not even remember. The brain is loosening its grip on the sleeping state. It's finishing its work. Not all at once, but in phases. The night shift is winding down. Files have been sorted. Emotions have been calibrated. Systems have been tuned. By the time your eyes begin to flutter open, much of what your brain has done overnight will be invisible to you. You won't remember the sleep spindles or the glymphatic waves or the micro-adjustments to hormone signaling. You may remember a dream or a fragment of one, but most of the night will feel like a blur, something that passed without your awareness. And yet, you'll feel different, calmer, clearer, more balanced. That's not magic, that's biology. That's the result of hours of non-stop activity performed quietly, reliably, and without your permission. The brain never truly rests, but during sleep it shifts gears in ways that allow your mind and body to stay functional, stable, and adaptable. It protects you from emotional overload. It helps you remember. It clears out waste. It regulates essential systems. It makes you more capable of facing the day ahead. This is the night shift. Unseen, mostly unfelt, but critical. Every hour you spend asleep is another hour the brain has to repair what was strained, to strengthen what was learned, and to prepare you, calmly, gradually, for the moment the light returns. By the time your brain enters the later stages of the night, it's already cycled through hours of behind-the-scenes activity. The deeper phases have taken care of essential repairs, immune regulation, and metabolic fine-tuning. But as the cycles continue, and REM sleep begins to take up more time, the brain shifts its focus again, this time toward integration. This is where dreams begin to dominate, where memory processing reaches new levels of complexity, and where the brain's version of housekeeping kicks into full gear. The idea that sleep is useful for memory isn't new, but only in recent decades have scientists been able to observe the brain in enough detail to begin understanding just how elaborate this process really is. While you sleep, especially during both deep non-REM and REM phases, your brain isn't simply reviewing information, it's organizing it, reshaping it, and deciding how it fits into everything else you already know. And it's doing this with astonishing selectivity. The day's experiences don't enter memory storage in a perfect line. They're not kept like files in a cabinet or videos in a playlist. Instead, they're fragmented, layered, emotional, contextual. Some are stored as facts, some as impressions. Others are altered, edited, or even discarded entirely. The brain decides which memories are important enough to keep, and which ones can fade quietly without consequence. This prioritization isn't random. It's influenced by emotion, repetition, novelty, and relevance to your existing knowledge. When something emotionally charged happens, a fight, a surprise, a moment of joy, it often leaves a stronger trace in your brain. That's partly due to the involvement of the amygdala, which flags emotionally significant events for priority processing. During sleep, particularly in REM, these flagged memories are revisited. Not always accurately, and not always in their original form, but with an eye toward integration. The memory may be softened, contextualized, or blended with other memories. Sometimes, it even shows up in dreams. Dreams are a major part of this cognitive activity, not just as a curious side effect, but as a potential tool your brain uses to test, rehearse, and reinterpret. While the precise function of dreams is still debated, a growing body of research suggests they play an important role in both memory consolidation and emotional regulation. During REM sleep, the brain becomes unusually active. Certain areas light up: the visual cortex, responsible for mental imagery, the limbic system, tied to emotion and memory, and the temporal lobes, which help process language and narrative. But the prefrontal cortex, the part of your brain responsible for logic, self-control, and rational thinking, is relatively quiet during this phase. That balance, active imagery and emotion, quiet judgment, creates the perfect conditions for dreams. In a dream, your brain can explore ideas without the usual constraints of reality. Scenarios unfold that never happened. People appear out of context. Time skips around. The impossible feels ordinary. This is partly why dreams are so difficult to remember or explain. They weren't built with coherence in mind. They were built with flexibility. This narrative looseness may allow the brain to combine concepts, test emotional responses, or simulate situations in a risk-free mental space. In one study, people were asked to solve complex problems before going to bed. Those who entered REM sleep were more likely to come up with creative solutions when they woke up, compared to those who remained in lighter sleep or stayed awake. The dreaming brain, free from distractions and rigid logic, seems to access associative networks in a way waking thought cannot. It doesn't think in straight lines. It loops, branches and weaves. This can result in nonsense, but it can also result in insight. Another theory proposes that dreams help your brain make sense of emotional experiences by replaying them in altered forms. You might dream about someone who upset you, but they appear in a different setting, or as part of an unrelated storyline. That dream isn't just random. It may be the brain's way of revisiting an emotional memory without triggering the full weight of the original feeling. Studies have shown that people who experience REM sleep after a traumatic event often report reduced emotional reactivity later. It's not erasure, it's processing. Quietly, gradually, the dream state helps the mind rebuild emotional equilibrium. This internal processing isn't always peaceful. Nightmares can occur when the emotional charge of a memory is too strong to be softened in one night. In these cases, dreams may reflect unresolved stress, anxiety, or fear. But even nightmares can serve a purpose. Some researchers believe they function as an adaptive response, a kind of mental rehearsal for threat recognition or emotional resilience. Recurring dreams, especially those linked to real-life stressors, may be your brain's attempt to work through something it hasn't yet resolved. Beyond dreams, other kinds of mental housekeeping are underway. During sleep, the brain doesn't just store new memories, it prunes and reorganizes existing ones. This process, known as synaptic downscaling, helps prevent your brain from becoming overloaded with information. While you're awake, the connections between neurons, called synapses, become stronger and more numerous. But not all of them are useful or sustainable. If the brain kept every single connection active, it would eventually become inefficient, noisy, and metabolically unsustainable. Sleep offers a solution. During certain phases, especially deep non-REM sleep, the brain downregulates less important synapses. It doesn't erase everything, but it quiets the unnecessary signals, trimming back the noise. This creates space, both physically and metabolically, for new learning the next day. It's a balancing act, a nightly reset that keeps your cognitive system flexible, adaptable, and ready for whatever comes next. Another subtle but crucial part of this process involves what's called memory integration. It's not just about remembering isolated facts or events. It's about fitting those memories into your larger understanding of the world. If you learn something new, the brain has to decide whether it confirms what you already believe, contradicts it, or requires the creation of a new category entirely. Sleep is when that work happens. The brain replays fragments of information and searches for where they belong. This might explain why we sometimes wake up with a clearer understanding of something we struggled to grasp the night before. The answer wasn't found during the dream, it was built during the night. Interestingly, the quality of this mental housekeeping can be affected by many external factors. Sleep deprivation disrupts memory consolidation. Fragmented sleep reduces REM cycles. Stress can interfere with the delicate timing of neurotransmitters needed for proper synaptic adjustment. Even the timing of your sleep, when you go to bed, when you wake up, how consistent your routine is, can influence how well your brain performs these tasks. The glymphatic system, which helps flush metabolic waste from the brain, also functions most efficiently during sleep. This includes the clearance of beta amyloid, a protein associated with Alzheimer's disease. Without sufficient deep sleep, this waste clearance is impaired. Over time, reduced efficiency in the brain's cleaning mechanisms may contribute to cognitive decline. This isn't to suggest that poor sleep causes neurodegenerative disease directly, but rather that sleep is part of a long-term protective system, one that needs to function consistently to support brain health across decades. In healthy sleepers, the brain navigates this entire process night after night, without conscious input. It doesn't need instructions, it doesn't wait for approval. It begins when conditions are right, and proceeds through cycles. Light sleep, deep sleep, REM, adjusting as it goes. Early in the night, deep sleep dominates. That's when the body repairs tissue, restores energy, and clears physical waste. Later in the night, REM takes over, That's when emotional balance, memory integration, and dreaming peak. Each cycle builds on the last. Each one pushes the brain a little further toward clarity, balance, and cognitive renewal. This whole sequence, dreams, memory consolidation, emotional reprocessing, neural pruning, is invisible. You don't feel it happening. You're not aware of the adjustments being made, but when you wake, the results are there. You remember things more easily. You feel less overwhelmed. Your mood has shifted, even if subtly. That's not just coincidence, that's mental housekeeping. The brain cannot afford to keep everything, so it sorts. What you dreamed about may not seem related to what happened during the day, but the connection is usually there, under the surface. A feeling you couldn't name, a conflict you didn't resolve, a question you weren't ready to ask. These are the threads that your brain follows at night, tugging gently at the tangled pieces until they make more sense. And then quietly the cycle continues. More spindles, more K-complexes, more REM. The brain isn't finished. It never truly is. But by morning, the most critical work is often complete. The filing is done. The dust has settled. The parts of the mind that held confusion or emotional weight have been given a little more space. When you finally wake, stretch, and rejoin the day, you're stepping into a world that your brain has spent the night preparing you for. Not just physically, but cognitively and emotionally. You're not the exact same person you were when you fell asleep. You're just a little more adjusted, a little more balanced, a little better equipped to take in the next round of experiences. And when the day is done, your brain will start again. It'll sweep, sort, soften, and store. It doesn't need a signal. It only needs time, quiet, and the darkness behind your eyes. By the time you've been asleep for just a few hours, your brain has already gone through several major shifts in state. It's handled memory replay, emotional processing, and the earlier stages of dream activity. But behind all of that, beneath the vivid mental imagery and the quiet orchestration of neurotransmitters, there's something even more basic happening. It's something most people don't think about. And yet it may be one of the most essential reasons we sleep at all. The brain during this time is cleaning itself. This is not a metaphor. The idea that sleep clears your head is not just a poetic phrase or a way to describe emotional relief. It's grounded in biology. Every hour you spend awake, your brain accumulates waste. Not garbage in the traditional sense, but molecular byproducts, bits and fragments left over from the intense energy demands of neural activity. Thoughts, decisions, learning, emotion. All of it costs energy. That energy expenditure generates waste. And while other organs have clear, well-mapped systems for dealing with that waste, the brain requires something a bit more specialized. During wakefulness, your brain cells are constantly active. Neurons fire rapidly, exchanging signals across vast networks. Supporting cells like astrocytes and microglia work to maintain balance. Blood carries nutrients in, oxygen fuels the activity, and every one of these processes creates leftover molecules, proteins, metabolites, oxidants, small invisible traces that collect in the spaces between cells. Over time, this buildup can interfere with healthy function. That's where sleep comes in. The system responsible for clearing out this waste is called the glymphatic system. It's a network of channels that allows cerebrospinal fluid, the clear liquid that surrounds the brain and spinal cord, to flow through the brain's tissues, flushing out debris. It's somewhat similar to the lymphatic system used elsewhere in the body, but with a few unique adaptations suited for the sensitive environment of the brain. And here's where it gets interesting. This cleaning process doesn't run at full power while you're awake. It waits. It activates most strongly when you're asleep, particularly during the deep, slow-wave phases of non-REM sleep. In this state, the brain undergoes subtle physical changes that allow for more efficient waste clearance. The cells actually shrink slightly, increasing the volume of interstitial space, the area between neurons, by up to 60%. That extra space creates room for fluid to circulate, carrying away waste products that would otherwise linger. This fluid, cerebrospinal fluid, or CSF, pulses gently through the brain, driven by slow waves of electrical activity. It moves in rhythm with your breathing and heartbeat, drawn into deeper tissues where it can collect waste and transport it out. The entire cycle is elegant, quiet, and automatic. You don't feel it. You don't control it. But it happens night after night, as long as sleep is allowed to do its job. One of the key molecules cleared during this process is beta amyloid, a protein that, in excess, can begin to form sticky plaques between neurons. These plaques are one of the defining features found in the brains of people with Alzheimer's disease. Tau protein, another marker associated with neurodegeneration, is also cleared more effectively during sleep. While the relationship between these proteins and cognitive decline is still being studied, the evidence suggests that impaired clearance, especially when sleep is chronically disrupted, could play a significant role in long-term brain health. This makes the nightly rinse cycle more than just maintenance. It's preventative. It's a kind of long-term investment. Your brain is making deposits into its own future stability by ensuring that metabolic waste doesn't build up to dangerous levels. When sleep is shortened, delayed, or fragmented, the efficiency of this clearance drops. That doesn't mean a single bad night will cause permanent harm. The brain is resilient. But over time, consistent sleep disruption may allow these waste products to accumulate in ways that gradually affect cognitive function. You may have noticed that after a night of poor sleep, your mind feels foggy. Tasks that were easy yesterday suddenly seem complicated. You forget where you placed your keys. You struggle to find words. This phenomenon, often called brain fog, is partly due to the cognitive and emotional effects of sleep deprivation. But part of it may also come from a more physical place. Excess waste lingering in the brain, interfering with optimal function. And it's not just proteins like beta amyloid or tau. The brain produces many other byproducts during the day, including reactive oxygen species, molecules that, in excess, can damage cellular structures. While antioxidants help manage these molecules, sleep appears to enhance that defense system. Certain genes associated with oxidative stress response become more active during sleep. It's as if the brain uses this time to run a systems check, identify problem areas, and deploy resources for repair. Meanwhile, glial cells, the support cells of the nervous system, ramp up their activity. Microglia, in particular, become more active in surveillance and cleanup. They help break down damaged cells, remove dead ones, and regulate inflammation. This is crucial, because even low-grade inflammation in the brain can begin to affect cognition, emotion, and sleep itself. Without regular, consistent rest, the brain's immune support begins to falter, and inflammation can become chronic, a risk factor not just for mental health issues, but also for neurological disorders. What's striking is how elegantly timed all of this is. None of it requires you to do anything consciously. You don't need to focus, you don't need to visualize it. The process unfolds naturally as part of the architecture of sleep. As long as the cycles are intact, the brain handles the work. One phase prepares the next. One task allows the next to proceed. It's a self-maintaining rhythm, as long as it's not interrupted too often or for too long. But modern life doesn't always make space for this kind of uninterrupted rest. Irregular schedules, artificial lighting, stress, late-night screen time, all of these can affect the timing and quality of sleep. And since the brain's cleaning system depends on reaching deep, consolidated stages, even small disruptions can reduce its effectiveness. Fragmented sleep, the kind caused by noise, shift work, or chronic insomnia, may leave the brain less able to clear the day's waste, especially in the long term. That's why regular sleep routines, consistent sleep windows, and protection from artificial light exposure late at night can all play a part in supporting brain health. The brain doesn't need perfect conditions, but it does need regularity. It needs the space to do its work. sleep researchers often emphasize the role of sleep pressure, the biological drive that builds the longer you're awake. It's regulated by substances like adenosine, which accumulates in the brain during wakefulness. Adenosine contributes to feelings of sleepiness, and it's believed to signal the need for rest. Interestingly, one of the things sleep does is help reset adenosine levels, another form of internal cleanup. That's partly why caffeine, which blocks adenosine receptors, temporarily reduces sleepiness. But it doesn't remove the buildup, it just masks it. Only sleep actually clears it out. This pattern, accumulation during wakefulness, clearance during sleep, is one of the most basic rhythms in the brain. It applies to waste, to stress, to memory fragments, and even to neural activity itself. Wakefulness is input, sleep is output, day is for collection, night is for cleaning. It's not always obvious how deeply this balance matters until it's disrupted. People who experience extended sleep deprivation sometimes report sensory distortions, memory lapses, and emotional volatility. These aren't just the result of fatigue. They may stem from the brain struggling to function under the weight of too much buildup and not enough time to restore itself. Animal studies have shown similar effects. In rodents, researchers have found that sleep deprivation can lead to excessive synaptic pruning, elevated inflammation, and impaired waste clearance. When the brain isn't given time to perform its maintenance tasks, it doesn't just become tired, it becomes disorganized. Communication between neurons falters, timing between brain regions drifts, and behavior begins to change in subtle but measurable ways. In contrast, even short periods of restorative sleep can begin to reverse those effects. The brain doesn't need perfection, it needs opportunity, a chance to reset its internal environment, sweep away the molecular clutter, and restore balance. It's easy to think of sleep as downtime, something unproductive, a pause in the day's activities. But from the brain's perspective, sleep is when the real work begins. The maintenance crew comes out, the filters turn on, the fluid begins to flow. It's a shift from doing to maintaining, and that maintenance makes all the doing possible again the next day. All of this is happening while you're unaware, while you're breathing slowly, lying still, dreaming or not dreaming. The cleanup doesn't ask for recognition. It doesn't leave a report. It just works, automatically, repeatedly, and with an elegance we're only just beginning to understand. When you sleep, your brain isn't checking out. It's checking in, running diagnostics, repairing damage, taking out the trash, and in doing so, it's keeping you clear, steady, and capable of returning to the world each morning with a mind that's ready to hold new thoughts, process new emotions, and meet new experiences. By the time your brain enters its first REM cycle, something fundamental has shifted. The slow, deliberate patterns of deep sleep have begun to give way to something livelier, stranger, and in some ways more familiar. Brain activity begins to resemble that of wakefulness. Neural circuits light up, electrical rhythms quicken, breathing becomes less regular, heart rate increases slightly. Your eyes, though closed, begin to dart rapidly from side to side beneath the lids. And all of this is happening while your body remains perfectly still. This is REM sleep, short for rapid eye movement, and it's one of the most distinctive and mysterious stages of the sleep cycle. Unlike deep sleep, where the brain's waves slow to a heavy coordinated rhythm, REM is characterized by high-frequency, low-amplitude activity. If you were to look at a scan of the brain during REM, you might think the person was awake, but they're not. They're somewhere else entirely. REM sleep usually begins about 90 minutes after you fall asleep, and becomes more prominent in the second half of the night. Early REM periods might only last a few minutes. Later ones can stretch to an hour. Across a typical night, the average adult cycles through 4 to 6 rounds of REM, increasing in length and complexity as morning approaches. So what exactly is happening during this time? And why does the brain dedicate so many resources to something we barely remember? To begin with, REM sleep is the stage most strongly associated with dreaming. That's not to say dreams don't occur in other phases, as they do, but REM dreams tend to be longer, more vivid, more emotional, and more narrative-driven. During this stage, the brain creates elaborate simulations of people, places, events, and ideas. Sometimes they make sense, sometimes they don't. But what's remarkable is the level of detail and structure these dreams often contain. This storytelling function seems to arise from a unique blend of brain activity. During REM, the visual cortex becomes highly active, generating imagery independent of external input. The limbic system, particularly the amygdala and hippocampus, becomes engaged as well, providing emotional content and memory fragments. Meanwhile, the dorsolateral prefrontal cortex, the area responsible for logic, self-monitoring and impulse control, remains relatively quiet. The result is a mental space where your brain is free to create without interruption. It can pull from memories, emotions, abstract thoughts, and recent experiences, combining them in ways that often defy the rules of time, space, and realism. People morph into other people. Locations shift without explanation. Conversations happen out of sequence. And yet, while it's happening, it feels real. The brain doesn't just accept this surreal narrative, it participates in it. You might feel emotions during the dream, respond to events, make decisions, even experience physical sensations. This immersive quality is part of what makes REM dreams so memorable, at least in the brief window after waking. But why would the brain bother with this kind of mental cinema? What purpose do dreams serve? There are several theories. One of the most prominent is that dreams help the brain process emotions. The amygdala's heightened activity during REM suggests that emotionally charged memories are being revisited and potentially modified. You may not relive a memory exactly as it happened, but you might encounter a version of it, abstracted, disguised, or blended with something else. This reprocessing allows the emotional charge to be diffused, similar to a form of exposure therapy. It's not about forgetting, it's about integrating. Another theory points to creativity. Studies have found that people woken from REM sleep perform better on tasks requiring abstract thinking, pattern recognition, or creative problem solving. The dreaming brain appears to explore concepts without the usual constraints, making connections between ideas that waking consciousness might overlook. In this view, REM sleep serves as a kind of overnight brainstorming session, a way for the brain to rearrange and remix information in search of insight. Memory processing is also a central feature of REM. While deep sleep helps strengthen factual and procedural memory, REM may help weave those memories into broader cognitive frameworks. It's not just about remembering that you studied a word or practiced a skill. It's about linking that information to other knowledge, emotions, and contexts. This integration makes memories more usable, more applicable, and sometimes more meaningful. There's also evidence that REM plays a role in social cognition, your ability to understand and predict the thoughts, feelings, and behaviors of others. Dreaming often involves social situations, real or imagined, filled with interaction, conflict, humor, affection, or awkwardness. These simulations may help the brain rehearse social responses, test emotional scenarios, or consolidate interpersonal learning. Essentially, the brain may be training itself for the emotional and relational challenges of daily life. Meanwhile, the body remains still. This is due to a phenomenon called rematonia, a temporary paralysis of most voluntary muscles. It's thought to prevent you from physically acting out your dreams. The brain activates motor regions during REM, just as it does during waking movement, but those signals are blocked in the spinal cord by inhibitory neurons. As a result, you might dream that you're running, speaking, or reaching for something, but your body doesn't move. There are exceptions, of course. In REM sleep behavior disorder, this paralysis doesn't occur properly, and people may physically act out their dreams, sometimes violently, often without awareness. This condition highlights just how active the brain is during REM. and how important that muscle inhibition is to keep dreaming confined to the mind. REM isn't evenly distributed across all ages or stages of life. In infants, REM sleep can make up over half of total sleep time. Their brains, undergoing rapid development, may use REM to support the formation of neural networks and the encoding of early experiences. As we age, the proportion of REM sleep decreases, though it remains essential for cognitive and emotional regulation well into adulthood. Disruption of REM sleep has been linked to a range of problems, from impaired memory and reduced emotional resilience to increased stress and anxiety. Certain medications, especially antidepressants and sleep aids, can suppress REM. So can alcohol. While these substances may help you fall asleep faster, they often interfere with the architecture of sleep, especially the later stages when REM tends to dominate. And because REM cycles get longer as the night progresses, anything that shortens sleep, early alarms, stress-related awakenings, or inconsistent bedtimes, can reduce the amount of REM you get. That's why extended, uninterrupted sleep is often necessary for the full benefit. If you cut the night short, you're missing out on the brain's most imaginative, emotionally rich, and cognitively integrative hours. For all its complexity, REM remains one of the most intriguing and least understood parts of the human experience. You don't control when it starts. You don't control what you dream about. And yet, these dream experiences can linger in your memory, influence your mood, and occasionally change the way you feel about something in waking life. They come from somewhere inside, not just random sparks of neurons, but a deliberate pattern of activity crafted by a brain that seems to know what it's doing, even when you don't. Some people experience lucid dreaming, a state in which the dreamer becomes aware they are dreaming and may even exert some control over the content. Lucid dreams typically occur during REM, and they suggest that self-awareness, though muted during sleep, can sometimes re-emerge. What triggers lucidity is still not fully understood, but it appears to involve partial activation of the prefrontal cortex, allowing for a layer of metacognition within the dream state. The potential of REM doesn't end with dreams. It extends into waking life in subtle ways. When you've had enough REM, you're more likely to feel emotionally balanced, socially attuned, and cognitively flexible. You may not remember the dreams themselves, but you carry their influence with you. In the ease of a conversation, the speed of a decision, the resilience of your mood. REM doesn't just entertain the sleeping brain, it prepares the waking one. And so, each night, your brain waits for the opportunity. It moves through its stages, light sleep, deep sleep, transitional waves, and when the time is right, it lifts the curtain. The theatre opens, the actors appear, scenes unfold, unbound by logic or time. Your brain becomes a midnight cinema, weaving images and feelings into stories that may never be told aloud. And when it's over, the body remains quiet, the curtain falls, and the brain prepares to do it all again, not for show but for survival. By the time the night has deepened and the early distractions of the day have faded into the background, your brain enters one of the most mysterious and essential states it's capable of producing. It's not dream-filled, not emotionally rich like our REM, not full of vivid scenes or shifting narratives. Instead, it is still, steady, and deeply rhythmic. This is what sleep researchers call slow-wave sleep, often referred to as deep sleep. And it's unlike anything else your brain experiences during the day. You don't remember being in it. You don't feel it starting or ending. But when you've had enough of it, you know. You wake up grounded, clear-headed, and able to function. When you haven't had enough of it, you feel it just as strongly, in the heaviness behind your eyes, in your mood, your reaction time, your focus, and even your ability to form new memories. Deep sleep, for all its quietness, is a foundation. And like any foundation, you don't think about it unless it's missing. Deep sleep is classified as stage 3 of non-REM sleep. It's also sometimes called slow-wave sleep because of the large, synchronized waves of electrical activity that flow through the brain during this stage. These waves, delta waves, are the slowest brain waves we experience, typically oscillating at less than 4 cycles per second. Compared to the faster, more chaotic patterns seen during wakefulness and REM, these are calm, rolling signals, like ripples moving in unison through vast networks of neurons. What these waves indicate is not the absence of activity, but the coordination of it. During deep sleep, millions of neurons begin firing in harmony, alternating between states of activity and silence. It's as if the brain is collectively breathing, a pulse that carries through the cortex down into deeper structures and back again. This coordinated activity is not random. It seems to provide the ideal environment for a wide range of critical biological and cognitive functions. One of the primary roles of deep sleep is physical restoration. During this stage, the brain directs the body to carry out cellular repair, muscle rebuilding, and tissue growth. Growth hormone, one of the key players in physical recovery, is secreted in high amounts during deep sleep. It's essential for healing wounds, repairing muscles after exercise, and maintaining overall metabolic health. This is part of why sleep is such an important factor in physical recovery. It's not just about rest. It's about active repair, directed from the brain down. But the effects of deep sleep go far beyond the body. The brain itself benefits from this stage in ways that are central to your ability to function cognitively. Memory consolidation, particularly for declarative memories, facts, events, concepts, is strongly linked to slow-wave sleep. When you learn something new during the day, your brain doesn't store it in one place right away. It encodes the information temporarily, mostly in the hippocampus, where short-term memory is processed. Then, while you sleep, especially during deep sleep, the brain replays these memory traces. It sends them from the hippocampus to the neocortex, where they're gradually integrated into long-term storage. This process is remarkably efficient. Brain imaging studies have shown that the same neural pathways activated during learning are reactivated during deep sleep, as if the brain is rehearsing, reinforcing, and solidifying the information in the absence of distraction. This isn't just theory. Experiments have demonstrated that interrupting slow-wave sleep, even without reducing total sleep time, can impair the ability to recall information learned the previous day. People who miss deep sleep don't just feel tired. They perform worse on tests, struggle with decision-making, and often report difficulty concentrating. The brain simply hasn't had enough time to stabilize what it learned. And it's not only memory that deep sleep helps. Emotional regulation is strongly influenced by this phase as well. While REM is known for emotional reprocessing through dreams, deep sleep appears to play a complementary role. It helps reduce the overall excitability of emotional circuits in the brain. After sufficient deep sleep, regions like the amygdala, responsible for fear and stress responses, become less reactive. People report feeling calmer, more even-tempered, and better able to handle minor frustrations. Lack of deep sleep, on the other hand, tends to amplify emotional responses. Minor setbacks feel overwhelming. Tolerance for discomfort drops. You may find yourself irritable, anxious, or easily discouraged, often without knowing why. The connection between poor sleep and mental health issues is complex, but deep sleep seems to function as a buffer, reducing baseline stress and giving the brain time to return to a more balanced state. Another function tied closely to this phase is the brain's unique cleaning system, the glymphatic system. During deep sleep, cerebrospinal fluid flows through the brain more freely, helping to clear metabolic waste products from the spaces between neurons. This includes proteins like beta amyloid, which, when allowed to accumulate, are associated with Alzheimer's disease. Deep sleep enhances the flow of this cleansing fluid by increasing the size of the interstitial spaces between brain cells, essentially allowing more room for fluid movement. The timing of this system is no accident. It's most active during the very stage of sleep, when overall brain activity is at its most synchronized and energy demand is lowest. In this sense, deep sleep functions like an overnight cleaning crew, entering the building once the lights have dimmed and the workers have gone home. It doesn't need supervision. It just needs time and quiet. Interestingly, deep sleep also appears to have an impact on immune function. During this stage, the brain signals the release of cytokines, small proteins that help regulate immune responses. Sleep deprivation, especially the loss of deep sleep, has been shown to reduce the production of these important molecules, weakening the immune system's ability to respond to infections. This may be one reason why people who are sleep deprived are more likely to catch colds and recover more slowly from illness. The immune system, like everything else, depends on time for restoration. From a neurological perspective, what's most fascinating about deep sleep is that it's not evenly distributed throughout the night. The majority of it occurs in the first few sleep cycles, typically within the first 3 to 4 hours of sleep. The brain seems to prioritize this stage early in the night, possibly because the processes it supports, memory transfer, immune priming, and physical repair, are so foundational to everything else that follows. As the night goes on, REM sleep becomes more dominant and deep sleep tapers off. That's part of why going to bed late, or shortening the first half of the night, tends to be more disruptive than waking up early. You're cutting into the portion of the night where the most intense restorative processes occur. Even if you sleep the same number of hours, shifting the timing can reduce the quality and structure of deep sleep. The amount of deep sleep you get also changes with age. In early childhood, it dominates sleep architecture. Infants and toddlers spend a significant portion of the night in slow-wave sleep, reflecting the rapid physical and neurological growth happening during those years. By adolescence, deep sleep still plays a major role, supporting learning and emotional development. But as people enter adulthood and especially older age, the proportion of slow-wave sleep tends to decrease. It becomes more fragmented. The waves become less synchronized. And while this decline is considered normal, it may also help explain why older adults are more susceptible to memory problems, immune challenges, and mood fluctuations. Lifestyle factors also play a role. Exercise, for instance, has been shown to promote deeper sleep. So has exposure to natural light during the day, and limiting artificial light exposure at night. On the other hand, substances like caffeine, alcohol, and some medications can reduce slow-wave sleep, even if total sleep time appears unaffected. Stress too can interfere with deep sleep. Elevated cortisol levels, the body's primary stress hormone, tend to delay sleep onset and reduce the amount of time spent in deep sleep. That creates a loop. Poor sleep increases stress reactivity, and stress reduces the ability to get restorative sleep. Breaking that loop often requires more than just a longer night. It requires consistency, environment, and sometimes lifestyle adjustments that give the brain what it needs to re-enter those deeper waves. What makes deep sleep particularly valuable is its silence. You don't wake up from it remembering anything. You don't dream, or if you do, those dreams are vague and minimal. There's no narrative, no emotional plotline, no strange symbols to decode. Just a pause, a powerful rhythmic quiet that gives the brain a chance to regroup. And yet, while you feel like nothing is happening, nearly everything is. Muscles are being rebuilt. Neurons are communicating in rehearsed patterns. Waste is being flushed. Stress is being reduced. Memories are being stabilized. The next day is being prepared for, not through action, but through alignment. You don't need to understand any of this for it to work. You don't need to track your brain waves or optimize your temperature or focus on your breathing. Your brain knows how to find this state. It's been doing it since before you could name it. All it requires is the time and the space to get there. And once you do, once the rhythm of slow waves takes hold, the brain goes about its business without you. It doesn't need your input. It only needs your trust and your sleep. After the quiet rhythm of deep sleep has finished sweeping through the brain, the effects linger. You don't notice them when you wake, at least not directly. But you do notice that your thoughts feel smoother, that the irritability from the day before is gone, or at least softened, that the things you needed to remember didn't slip away, and all of that is because while you were resting, an invisible team was at work. Sleep functions like a full-service maintenance crew for the brain. Not a single task, but a layered, well-organized system of repairs, cleaning, sorting, calibration, and restoration. Each stage of sleep contributes something unique to this operation, and together, these stages form a nightly ritual that keeps the brain not just alive, but functional, flexible, and prepared for another day of consciousness. The crew doesn't operate in a straight line. It doesn't tackle one problem at a time. Instead, it rotates its focus, moving through repeating cycles roughly every 90 minutes. Within each cycle, there are shifts in neural activity, hormone levels, blood flow, immune signaling, and chemical balance. From light sleep to deep, slow-wave sleep to REM, each phase targets a different part of the brain's needs. Imagine the first part of the cycle as basic preparation. You're falling asleep. Light sleep begins, your body temperature starts to drop. Muscle activity slows. The mind becomes less reactive to outside stimuli. This is when the maintenance crew first clocks in, taking note of what the day has left behind. It doesn't start working yet, but it gets into place. It checks systems. It observes. It prepares. Then, as you move into deeper sleep, real work begins. Brain waves become slower and more synchronized. The energy demands of wakefulness disappear. That drop in activity creates an opening, a window of time and stillness when repairs can begin. During this phase, glial cells, which support and insulate neurons, become more active. The glymphatic system increases in flow. Waste products begin to drain. The environment between brain cells, which shrink slightly while you're awake, opens up again. That extra space allows cerebrospinal fluid to wash over neural tissue, carrying away molecular debris. This flushing process isn't random. It targets the proteins and metabolites that build up during normal waking activity, including beta amyloid and tau, both of which are associated with neurodegenerative diseases when allowed to accumulate. While you sleep, your brain is literally cleaning house. It's using a method so efficient, so automatic, and so completely beyond your awareness that for a long time, science didn't even know it existed. The slow, synchronized brain waves of deep sleep don't just signal this cleaning, they help drive it. Those waves create pressure changes that seem to move cerebrospinal fluid in and out of brain tissue, in time with the pulsing of neurons. It's like a gentle, rhythmic tide, directed not by any external force but by the brain's own internal patterns. At the same time, the immune system is getting its instructions. Sleep regulates the production of cytokines, the molecules that help coordinate immune responses. During deep sleep, these signals increase. They help promote inflammation where it's needed and reduce it where it's not. They also influence microglia, the brain's own immune cells, which move through neural tissue looking for damage, infection, or debris. When the body is sick, the brain adjusts its sleep patterns to produce more of these immune signals, often increasing the amount of deep sleep. Meanwhile, another team begins reviewing the data. Everything you took in during the day, from information to emotions, is up for review. This part of the maintenance crew isn't cleaning or repairing, it's sorting and organizing. The hippocampus, where short-term memories are held, replays key events. These events are then relayed to the cortex, where long-term memories are stored. This process doesn't involve you. It isn't something you can feel, but it's happening all the time in the background, as the brain decides what to keep, what to let go, and how to fit everything into your existing mental framework. Not every memory is preserved. Many are trimmed away, not because they're bad, but because they're unnecessary. The name you saw on a billboard, the exact layout of a room you passed through, the sound of a door closing. All of this may be registered at the time, but it doesn't all need to stay, so the brain filters. It strengthens connections that matter and weakens the ones that don't. It uses sleep as an opportunity to reduce clutter. The next phase of the cycle brings on REM sleep. This is where the crew changes shifts. It's still maintenance, but the focus turns inward. neural activity increases again, resembling wakefulness in some areas. Blood flow is redirected, brain temperature rises slightly, dreams begin to emerge, and while this might seem like a break from work, it isn't. The REM crew is focused on emotional regulation, creativity, and the linking of complex memories. During REM, the amygdala, the brain's emotional centre, becomes more active. So does the visual cortex. The prefrontal cortex, which handles logic and impulse control, remains relatively quiet. This allows for free association, the generation of ideas and scenarios without strict rules or filters. The brain explores different emotional contexts, simulates social interactions, replays events with symbolic overtones. It's a strange kind of psychological rehearsal, one that allows the mind to test itself against difficult feelings, interpersonal dynamics, or even internal conflicts. The maintenance here is less about removing waste and more about resolving tension. The brain uses REM sleep to defuse stress, process fear, and sometimes soften the emotional tone of certain memories. This is why you can go to bed feeling overwhelmed and wake up feeling not fixed, but better. The dream didn't solve the problem, but the REM cycle may have lowered the intensity of your reaction to it, making it easier to face, and then the cycle begins again. Light sleep returns, body temperature adjusts, muscles twitch slightly. Then, if you're not interrupted, you descend again into deep slow-wave sleep. The crew returns, cleaning continues, memories are replayed, emotional edges are filed down. Each 90-minute pass brings another layer of maintenance, another round of invisible work. It doesn't always go perfectly. Interruptions, whether from noise, discomfort, stress, or internal signals, can break the cycle. When that happens, the crew doesn't stop entirely, but it loses time. The brain tries to compensate in future cycles. Sometimes it prioritizes deep sleep if you've missed it recently. Other times, it pushes you faster into REM, but the balance is delicate. Repeated disruptions, even short ones, can reduce the effectiveness of this maintenance process over time. Chronic sleep deprivation, or even just irregular sleep, can leave some of the crew's work unfinished. Waste products aren't fully cleared. Memory consolidation is incomplete. Emotional processing stalls, and gradually the effects begin to accumulate. You may notice increased forgetfulness, a shorter temper, more frequent illness, less energy. These aren't just signs of a busy life. They're signals that the brain's nightly work hasn't been given enough room. The good news is that the maintenance crew is patient. Give it a chance, and it will resume its duties. Even a single night of high-quality sleep can begin to reverse some of the short-term effects of deprivation. The crew doesn't hold grudges. It doesn't need an apology. It just needs time and space to work. There's no way to artificially speed up this process. No shortcut that replaces the structure of a full night's sleep. Naps can help, so can brief rest periods, but they aren't a full substitute for the carefully layered repair and regulation that the brain performs each night. Sleep is designed to work gradually, through repetition. Its benefits are cumulative, not instant. And they're not only internal. The work that the maintenance crew performs overnight supports every outward-facing function you have. Attention, speech, movement, emotional stability, problem-solving, creativity. Even basic perception is sharpened when the brain has been allowed to tune itself overnight. The way you experience the world depends in part on whether the previous night gave your brain time to reset. This is why long-term studies show consistent sleep patterns are one of the best predictors of cognitive health in older adults. It's not just about how long people sleep. It's about how often their brains are given uninterrupted access to these internal maintenance cycles. In some ways, sleep is less about recovery from the day and more about preparation for the next one. When you fall asleep tonight, you won't need to instruct your brain to start cleaning. You won't have to tell your immune system to reset. You won't consciously decide which memories to keep. That's all handled for you, quietly, automatically. with a precision that no technology can replicate. The crew will return, the waves will begin, the circuits will hum, the fluids will flow, and the stories will play out behind your eyes. You won't feel it, you won't hear it, but your brain will be at work as it always is, maintaining the most complex system in the known universe without ever asking for recognition. Each day, whether or not you intend it, your brain collects things. Conversations, numbers, sounds, images, ideas, fragments of experience that are picked up almost constantly, like static sticking to fabric. Some of these experiences are deliberate. You study a fact, remember a face, repeat a name. Others are passive, a passing comment, the layout of a hallway, the scent of something cooking, and somehow, when the day ends, your brain knows that not all of it is worth keeping. It doesn't need every detail, but it also can't afford to lose something important. So during sleep, it begins a process that's quiet, invisible, and far more sophisticated than simple storage. It replays what happened, not in full, not with perfect fidelity, but in patterns, in waves, in fragments. This is memory replay, and it's one of the most remarkable things your brain does each night. You don't experience it consciously. Memory replay doesn't feel like remembering. It happens while you're asleep, often in the deeper phases of non-REM sleep, when you aren't dreaming in vivid images or stories, but your brain is active. Certain neural circuits light up in the same order they did when you were awake. It's like pressing the rewind button on your day, but with a purpose. In the hippocampus, a seahorse-shaped structure deep in the brain, neurons fire in sequences that echo what you were doing hours before. If you were navigating a new environment, solving a problem, learning a list, or experiencing something emotionally important, the patterns of activity from those moments are played back during sleep. They're not perfect recordings. They're simplified traces like sketches of the original events, but they're enough. These replays serve multiple functions. One is consolidation, the transfer of short-term memory into long-term storage. Your hippocampus is a temporary holding center. It can capture new experiences quickly, but it's not meant to store them permanently. For that, the brain needs to move them to the cortex, where more durable memories are built. Memory replay helps this transfer happen. It activates both the hippocampus and specific regions of the cortex at the same time, strengthening the connections between them. The more often this happens, the more stable the memory becomes. This process isn't limited to facts or events. It also applies to skills. If you've ever practiced a physical task, playing an instrument, typing a new sequence, learning a movement, your brain replays those patterns too. Motor areas of the brain light up in the same order they did when you were practicing, and remarkably, this seems to improve performance. People who sleep after practicing a skill tend to do better the next day than those who stay awake. The brain is refining its instructions, repeating the sequence, making it more efficient. There's also a kind of filtering happening during this process. Not all memories are replayed. The brain chooses, and what it chooses to replay depends on several factors: novelty, emotional impact, repetition, and relevance to existing knowledge. A new piece of information that connects well with something you already know is more likely to be integrated. A moment that carried emotional weight, even subtly, is more likely to be reviewed. The brain isn't just saving data, it's evaluating, deciding what matters. That evaluation is not perfect. Sometimes, important memories don't make it into long-term storage. Sometimes trivial details do, but overall the process is efficient. It leans toward what is most likely to be useful, even if you don't realize it. And it does all of this without your awareness, while you lie still, disconnected from the external world. The timing of memory replay appears to be tied closely to slow-wave sleep. During this phase, the brain produces large, coordinated waves of electrical activity that create windows for communication between the hippocampus and cortex. These windows are brief, sometimes just fractions of a second. but they're enough for replay to occur. And they happen repeatedly, hundreds of times across the night. Each replay strengthens the memory a little more. It's a gradual process. One night of sleep might not lock in a memory forever, but it starts the process. Repeated nights reinforce it. That's part of why distributed learning, studying a little each day over time, tends to be more effective than cramming. The brain needs time, and replay needs repetition. Without sleep between learning sessions, the consolidation is weaker. This might explain why people who are sleep-deprived struggle with recall. Their brains haven't had enough opportunity to stabilize the memory. It's not just a matter of being too tired to remember. The memory itself may not have been fully built. There's also evidence that replay helps the brain generalize. That is, it doesn't just reinforce specific facts, it helps find patterns. If you learn several things that are related, the brain may replay them together, identifying what they have in common. Over time, this leads to insights, a deeper understanding of how things are connected. Sleep researchers believe this may be one of the ways the brain builds conceptual knowledge, not just what you know, but how the pieces fit. Replay also seems to support emotional learning. The brain doesn't treat all memories the same. Events that involve strong feelings, fear, joy, embarrassment, pride, tend to leave deeper traces. During sleep, these traces are often replayed with emphasis. Emotional centers of the brain, like the amygdala, become more active, especially during REM sleep. But in non-REM sleep, emotion and memory also interact. The content may not appear as dreams. It may just be patterns, subtle, quiet reenactments that allow the emotional weight to be processed, and in some cases reduced. This can have real effects. People who sleep after a stressful event often report feeling less overwhelmed the next day. The memory is still there. The facts haven't changed, but the emotional intensity has shifted. That shift might begin with replay, a kind of background recalibration that makes room for perspective. It's worth noting that replay doesn't guarantee memory. You've likely forgotten countless things you learned, heard, or experienced, even after sleep. The brain is selective. It has to be. There isn't enough space or energy to hold on to everything. Replay is part of how it decides what to keep, and that decision is influenced by what you pay attention to, how often you revisit something, how emotional it is, and how well it fits into what you already know. Some researchers have even suggested that conscious reflection before sleep, thinking briefly about what you want to remember, may increase the likelihood of replay. The brain doesn't take orders exactly, but it seems to respond to cues. What you focus on has influence. If a memory is tagged as important, even subtly, it may get another chance to be processed. Replay isn't only about memory strength, it may also support flexibility. The brain doesn't just repeat experiences during sleep, it sometimes recombines them. A memory from the afternoon might be replayed alongside something from weeks ago. These connections can form new associations, new ideas, even dreams. This blending can lead to insight. It can also help the brain adapt, taking separate pieces and forming something useful. Animal studies have confirmed that replay isn't unique to humans. In rats, place cells, neurons that activate when the animal moves through specific parts of a maze, are reactivated during sleep in the same sequence as during the run. In some cases, the replay is even faster, as if the brain is compressing the experience to fit it into a short burst of activity. And sometimes, the sequence is replayed in reverse, possibly reflecting reflection or consolidation from goal to start. Human studies are more complex, but imaging and EEG research has shown similar reactivation patterns, and the more replay that's observed, the stronger the memory tends to be later. Replay isn't just a side effect of sleep, it's one of its central functions. What's extraordinary is how silently this all happens. You might go to bed thinking your day is over, that nothing more will be done, but your brain is reviewing, refining, reorganizing. It's playing through the soundtrack of your experiences, strengthening the melodies worth keeping, fading the ones that don't serve you. It's not doing this randomly. It's doing it with precision and with a sense of purpose shaped by evolution, survival, and the need to make sense of the world. You don't have to manage any of it. You don't need to set reminders or make lists or mentally rehearse your memories. Once you've given your brain the time and space, it knows what to do. Replay happens whether you believe in it or not, whether or not you remember your dreams, whether you're a student, an artist, a scientist, or someone just getting through the day. The brain does its work because it has to. It's built that way. And when you wake, what you've learned is a little more stable. What you felt may be a little less sharp. A name, a detail, a direction, now easier to retrieve. The connections may be a little clearer, not because you tried harder, but because your brain used the time you gave it. This is what sleep does. It doesn't just shut the system down. It runs the most essential programs in the background, cleaning, repairing, and quietly replaying the pieces of your life, one memory at a time. Throughout the day, your brain is constantly taking in emotional information. It's in the tone of someone's voice, the look on a stranger's face, a headline you didn't expect to read, the quiet reaction you had to something you saw but didn't say aloud. Some of it is subtle, some of it lingers, and you don't get to control how much of it follows you around. What sleep offers, not as a cure, not as a shortcut, but as a process, is a way for the brain to begin sorting through that build-up, not to forget it, not to suppress it, but to rebalance it. From the moment your eyes close, the brain begins changing how it handles emotion. The first stages of sleep reduce your sensitivity to external stimulation. You stop reacting to every sound or shift in temperature. But more importantly, the internal emotional circuits begin to shift too. Activity in the amygdala, the structure deeply involved in fear, stress, and threat detection, starts to change. The balance of neurotransmitters adjusts. Cortisol, the body's stress hormone, gradually declines. The whole emotional system begins to cool down. This doesn't mean you stop feeling. Sleep doesn't erase emotional experiences, but it changes the way the brain processes them. During deep sleep, for example, the neural activity is highly synchronized. Regions that often act independently during the day begin working together. This synchronization is thought to support emotional unlearning, a process in which the brain re-examines and reduces the emotional weight of experiences without removing the memory itself. This is particularly important after events that provoke a strong reaction, a moment of embarrassment, a flash of anger, something that caught you off guard. These leave an imprint. If you go to sleep soon after, your brain has a chance to begin deactivating the emotional charge around that memory. The event is still remembered, but it's less likely to trigger the same visceral reaction the next day. This is why people often say things feel better in the morning. It's not just a figure of speech, it reflects real neurochemical changes in how the brain is handling that memory. REM sleep also plays a unique role in this process. Unlike the deep stages that are quieter and more synchronized, REM is marked by bursts of activity in the brain's emotional and sensory centers. The amygdala becomes more active. The visual cortex lights up. But the prefrontal cortex, responsible for logic and restraint, stays relatively quiet. This creates a condition where emotional content can be reprocessed without the tight controls of daytime thought. It's during REM that the brain may be revisiting emotionally charged memories, playing them out in dreams, and gradually desensitizing itself to them. There's evidence that REM sleep helps reduce the intensity of traumatic memories. In sleep studies involving participants who viewed disturbing images or experienced stress, those who got full nights of sleep, especially including REM, reported lower emotional reactivity the next day. The images were still remembered, but the feelings they provoked were less intense. The same was not true for those who were deprived of RM. This doesn't mean sleep is therapy. It's not replacing the need for processing, talking, reflecting, or working through difficult experiences in waking life, but it does seem to create a kind of emotional buffer, a cushion of neural activity that gives the brain a chance to soften the edges, ease the pressure, and regain perspective. Without this buffer, things start to feel sharper, not more vivid, more volatile. You may have noticed how a night of poor sleep can leave you emotionally off balance. Minor frustrations become major irritants. Rejections feel more personal. Worries spin faster. That's not just because you're tired. It's because the brain hasn't had a chance to recalibrate its emotional systems. One study found that sleep-deprived individuals showed up to 60% more reactivity in the amygdala when shown emotional stimuli compared to those who had slept well. At the same time, communication between the amygdala and the prefrontal cortex was significantly weakened. In other words, not only was the emotional system more sensitive, it had less regulation. The result was an increase in impulsivity, mood swings, and distorted judgment. This might explain why sleep disruption is so closely linked to mood disorders. People with anxiety, depression, and bipolar disorder often experience sleep disturbances as both a symptom and a contributing factor. It's not entirely clear which comes first, but the relationship is clear. Poor sleep makes emotional regulation harder, and when emotional regulation falters, sleep tends to suffer. Breaking that cycle, even slightly, can make a meaningful difference. It's not just negative emotion that gets thrown off. Sleep deprivation also dulls the brain's response to positive stimuli. In experiments where participants were shown pleasant images, offered rewards, or asked to rate enjoyable experiences, those who were sleep deprived consistently reported lower levels of enjoyment. Brain scans confirmed a blunted response in reward-related circuits like the ventral striatum. The result is not just increased negativity, it's a loss of emotional range, a kind of numbness that makes everything feel flatter. By contrast, sufficient sleep appears to restore balance to the entire emotional spectrum. It doesn't make problems disappear, but it makes reactions more proportional. Joy becomes easier to feel, frustrations become easier to manage. The middle ground, where most of life takes place, becomes easier to inhabit. This is especially important in children and adolescents, whose brains are still developing their emotional systems. For them, sleep is not only a recovery mechanism, it's a training ground. Emotional memories, social experiences, and regulatory circuits are all still forming. Disruption to sleep during these stages can have long-term effects on emotional stability, attention, and even interpersonal relationships. Even in adults, consistent sleep plays a role in how emotions are expressed and managed. People who sleep well tend to have better empathy, more stable moods, and stronger coping skills. They also tend to recover faster from emotional setbacks. Their systems return to baseline more easily after being triggered. Again, this doesn't mean they avoid stress. It means their brains are better at handling it. The reason for this may come down to integration. During sleep, particularly REM, the brain integrates emotional memories with other types of information. It links feelings to context. It builds understanding. It updates the emotional database with new entries. This doesn't require effort. It happens automatically. But the result is a more coherent picture of emotional life. Less fragmentation, fewer extremes, more flexibility. It's worth noting that emotional processing doesn't require you to remember your dreams. In fact, most people don't. But that doesn't mean the brain isn't working through something. Just because the content isn't accessible doesn't mean the function isn't happening. The reduction in emotional reactivity, the improvement in mood, the recalibration of judgment, these happen even when the dreams themselves are forgotten. This may also explain why chronic insomnia can have such widespread effects on mental health. When sleep becomes fragmented or difficult to maintain, the emotional systems never fully shut down. The amygdala stays on high alert. The prefrontal cortex doesn't have a chance to reset. Over time, this leads to cumulative stress, not just psychological but physiological. Cortisol levels remain elevated, heart rate variability declines, the entire stress response becomes less flexible. And that inflexibility shows up in behavior, mood, and even physical health. Unfortunately, sleep is resilient. Emotional balance doesn't require perfection. It requires consistency. Even small improvements in sleep quality, going to bed a bit earlier, limiting blue light before sleep, creating a quiet and cool sleep environment, can lead to noticeable changes in mood and emotional regulation. The brain responds quickly to restoration. It wants to find balance, and when it does, you feel it. You might not notice the absence of anxiety, but you notice the ease of attention, the return of humour, the sense that problems, while still there, don't feel overwhelming. That's not sleep-fixing emotion. That's sleep letting the brain do what it was built to do: regulate, adapt, and recover. This doesn't mean that every night delivers full emotional repair. Some memories take time, some feelings linger, but the process begins each night you give it a chance. With each REM cycle, each wave of non-REM synchronization, your brain is doing its version of emotional hygiene, tidying up, reassessing, and where possible letting go. You don't need to plan this. You don't need to focus on it. Sleep is not a task you have to complete perfectly. It's a state the brain knows how to use. You just need to give it enough time, and in return it gives you the ability to face the next day with a mind that's slightly more balanced, more responsive, and more resilient than it was the day before. Each day brings with it more than you realize: new information, patterns, names, routines, bits of language, subtle rules of behavior. Even when you don't think of yourself as learning, your brain is learning. It's observing, absorbing, and making predictions. Sometimes that learning is deliberate. You study something, rehearse it, practice it. But much of it is incidental. The human brain is wired to adapt, whether or not you're trying. But learning doesn't stop when the day ends. In many ways, that's just the first step, because what happens during sleep is just as important, and sometimes more important, than what happens while you're awake. Sleep isn't a break from learning. It's when the real refinement begins. The brain has its own version of a learning lab, a place where memories are reviewed, skills are rehearsed, and concepts are connected. But instead of lab coats and chalkboards, it uses patterns of electrical activity, bursts of chemical signalling, and carefully timed reactivation of neural circuits. And the lab only opens once you've gone to sleep. This process begins early in the night, especially during the deep stages of non-REM sleep. Here, large, slow brain waves sweep across the cortex in highly synchronized patterns. These waves aren't just background noise. They create windows, brief, repeating opportunities for communication between the hippocampus, where recent memories are stored, and the cortex, where long-term memories are built. During these windows, the brain does something remarkable. It replays. The same neurons that were active during learning start firing again, often in the same sequence. This isn't passive replay, it's targeted. If you practiced a new skill, reviewed a new fact, or encountered a novel idea, that experience is now being revisited in miniature. Not with full awareness, not with images or inner monologue, but with structure, precision, timing. Replay helps stabilize these experiences. It strengthens the synaptic connections involved. It pushes memories out of short-term storage and into more durable networks. But that's just the beginning. Because sleep doesn't just preserve knowledge, it also transforms it. One way it does this is through integration. While you're awake, you can only focus on a limited amount of information at once. You're busy navigating the moment. But during sleep, the brain has the freedom to cross-reference. It compares new memories to older ones. It finds similarities. It spots patterns. It looks for contradictions. In doing so, it can build more general rules, the kind that help you understand not just facts, but systems. This is part of what makes sleep essential for problem solving. In studies where participants are given a complex task like solving a puzzle or detecting a hidden rule, those who sleep before attempting it again often perform better. They're not just better rested, Their brains have had time to process the underlying structure of the task, to move from surface details to deeper insight. That insight doesn't always feel like something you learned. It can feel like intuition, a hunch, a sense of knowing how to proceed. But underneath that feeling is a network of adjustments the brain made while you were asleep. It reviewed what didn't work, it traced through alternative solutions, and it did this without your conscious input. Learning through sleep also applies to language. When you're exposed to new vocabulary or grammar rules during the day, the brain doesn't immediately lock it in, but sleep gives it a chance to take hold. Neural representations of words become more stable. Pronunciation patterns are refined. Even the rhythm and tone of a language can be improved with sufficient sleep. Musicians too show this effect. Practice during the day is important, but the actual improvement, the speed, accuracy and fluency, often appears after a night's sleep. The motor cortex, which handles movement, appears to benefit from overnight reactivation. The same applies to athletes learning new movements, dancers refining timing, or anyone training a skill that combines physical coordination with mental precision. And it's not just about making what you've learned stronger. Sometimes the brain uses sleep to make it cleaner. It trims away unnecessary parts. If you learned multiple versions of a task, some correct, some incorrect, sleep helps suppress the errors. Not instantly and not perfectly, but over time, the cleaner version is reinforced. The noise is reduced. This refining process is also what helps prevent overload. If you learned everything equally, if every memory, every detail, every failed attempt stayed equally strong, your brain would quickly become overwhelmed. You'd have no way to distinguish useful knowledge from irrelevant noise. Sleep solves this by organizing. It keeps what fits, it deletes or suppresses what doesn't, and in doing so, it preserves mental space. Interestingly, this organization doesn't always require reinforcement. Sometimes people perform better on a test after sleep even if they haven't reviewed the material. That suggests that the brain isn't just relying on practice, it's working with what it already has, refining it internally. Sleep also appears to help with creative learning, not just repetition and recall, but insight and synthesis. When asked to come up with novel solutions, generate metaphors, or connect ideas in unusual ways, people often perform better after sleep. This is likely due to REM sleep, where the brain's associative networks become more flexible. During REM, connections are formed more freely. Concepts that are usually distant in your waking mind can suddenly appear side by side. That may be why dreams sometimes present strange combinations of people, places, and ideas. The brain is testing connections. Most of them don't make sense, but sometimes those combinations reveal something useful, a new way of seeing a problem or an emotional truth you hadn't considered. Researchers have studied this by waking participants during REM sleep and asking them to solve creative problems. In many cases, people are better at thinking outside the box when emerging from REM. It's not because they dreamed the solution, it's because their brains have spent time reorganizing ideas in a way that allows unexpected connections. None of this requires you to be aware. You don't need to visualize what you've learned or mentally rehearse before sleep, though doing so may help nudge the brain towards certain content. But even without effort, your brain is doing the work. The learning lab opens and the systems begin their cycles. Sleep also interacts with attention. During the day, you can't learn what you can't notice, and sleep plays a major role in determining what your brain is able to focus on. After good sleep, attention is sharper, distractions are less intrusive, and the mind can sustain effort for longer periods. That means new learning is more efficient, and that in turn gives the brain more meaningful material to work with during the next night's sleep. The cycle continues. Learn, sleep, consolidate, repeat. Even emotional learning follows this pattern. You might not think of emotion as something you can learn, but the brain treats emotional experiences much like cognitive ones. It tries to make sense of them. It assigns meaning. It connects them to prior events. And just like factual knowledge, those emotional lessons become more stable after sleep. If something upset you, a conversation, a mistake, a disappointment, sleep can help you not only recover, but understand. The event may be reviewed, reinterpreted, or softened. The connections between that feeling and past experiences may be adjusted. You may not wake with a full explanation, but you may feel that something inside has shifted. That's not an illusion. It's the effect of overnight learning applied to emotion. And when it comes to unlearning, sleep helps there too. If you've formed an association that no longer serves you, a habit, a fear, a belief, the brain can begin dismantling it during sleep, especially if you've started to challenge that belief during the day. Sleep strengthens new learning, but it also helps weaken outdated patterns. This ability to reshape internal models, to refine how you see the world, is part of what makes sleep a learning system, not just a storage system. It doesn't freeze the past in place, it revises it. That revision happens slowly. It may take multiple nights, but each time you sleep, your brain is revisiting what you've learned and asking, does this still fit? And if it doesn't, the brain adjusts, quietly, without fanfare, without conscious intervention. You'll notice it only later when a concept that once felt confusing now makes sense, when a skill becomes smoother, when a feeling that once took over now feels manageable. Those aren't accidents. They're the result of a process you never felt, a process your brain carried out while you rested, without asking for anything in return. All you had to do was sleep. Not everything is meant to stay. That's a truth the brain understands more deeply than you ever need to. Each day you're exposed to more stimuli, more details, more experiences than any system could possibly hold on to. And yet, somehow your mind doesn't drown in this sea of information. You don't carry every glance, every sentence, every passing impression. What's kept is filtered, selected, made useful. What isn't is let go. Sleep is when that quiet sorting happens. While you rest, your brain does something far more complex than simply storing memories. It evaluates, it reviews, it reorganizes, it clears space. The content of your day, facts, observations, feelings, habits, sensory data, is brought before a kind of internal triage. What matters? What's worth reinforcing? What can be deleted? This process doesn't rely on you. It doesn't require you to consciously prioritize or rank your thoughts before bed. The brain has evolved to do this automatically, guided by a set of internal criteria, some obvious, some hidden, all incredibly efficient. And it starts early in the night. Deep sleep is where the heavy lifting begins. In this phase, large, slow waves move through the cortex in organized pulses. It's during these waves that neurons alternate between firing and silence, and during those moments of stillness, decisions are quietly made. The hippocampus, a key player in short-term memory, begins sending information out. Details are passed from this temporary storage area to other parts of the brain, particularly the neocortex where long-term memory lives. This handoff isn't immediate. It takes time and repetition. But while it's happening, the brain uses patterns to decide what should be transferred and what shouldn't. Novelty matters. So does repetition. So does emotional relevance. A surprising interaction, a meaningful experience, something that connects to what you already know. These things tend to be replayed more often during sleep. And the more they're replayed, the stronger their connections become. The stronger the connections, the more likely the memory is to persist. But not everything makes it through. Much of what happens during the day is never replayed. It's experienced once and then forgotten. This isn't failure, it's function. Without forgetting, the brain would be overloaded. If every trivial detail were stored, every time you looked at a clock, every commercial you glanced at, every redundant conversation, your ability to find relevant memories would decline. You'd remember too much of what doesn't matter and not enough of what does. This is why forgetting is not a flaw of memory but a feature of it. The brain has built-in mechanisms for reducing noise. Connections that aren't reinforced begin to weaken. Synapses lose strength. Eventually, those traces fade. You don't notice this happening. You simply stop recalling certain things. That's the signal that the memory has been allowed to fade, and sleep is a key time when that process is set in motion. Interestingly, the brain may not delete information immediately. Some forgotten material lingers in a kind of low-access state. Not gone, but difficult to retrieve. Only with time and disuse does it vanish completely. And some memories, once thought forgotten, can be reactivated with the right cue. This suggests that the brain doesn't just erase data, it compresses it, deprioritizes it, or buries it under newer connections. But the act of deciding what gets buried and what gets promoted is constantly influenced by sleep. The longer and deeper the sleep, the more time the brain has to run this process. The more consistent the sleep pattern, the more predictable and efficient this sorting becomes. Irregular sleep, by contrast, tends to disrupt the balance. Important memories might not be reinforced. Trivial ones might stick longer than they should. The structure begins to wobble. Another part of memory management is categorization. The brain doesn't just store facts as isolated pieces, it places them in context. Concepts that are related become linked. Skills that rely on each other are bundled. Emotional experiences are filed with sensory ones. And over time, these categories shape how you think. Sleep plays a major role in this. During REM sleep, especially, the brain appears to strengthen associative networks. This means it's not just storing facts, it's figuring out how they relate to other facts. You may not realize this is happening. You may wake with no awareness of these shifts, but over time, they change the way you process information, the way you interpret new input, the way you recognize patterns. This process is why sleep enhances insight. It's not just that you remember more, it's that your memories are more organized. They're easier to navigate. They're better connected, which means you can draw on them more effectively, even if you're not aware that you're doing so. There's also a role for sleep in removing redundancy. If you've learned something one way and then learned it again in a slightly different form, the brain may consolidate those two versions into one cleaner version. This streamlines storage, it reduces cognitive load, and it prevents confusion between similar inputs. For example, if you practiced a physical skill and then received feedback, your brain may reconcile those two versions overnight. If you heard a fact stated slightly differently by two people, the brain might integrate the core idea and discard the redundant phrasing. This kind of refinement is subtle. You don't remember making the edit, but the next time you use that knowledge, it comes out smoother. And just as sleep consolidates information, it also stabilizes it. Once a memory has been successfully transferred from short-term to long-term storage, it becomes less vulnerable to interference. This is part of what makes sleep after learning so important. It doesn't just make the memory stronger, it makes it more resilient. Without sleep, new memories are fragile. They're more easily lost. Even a few hours of wakefulness after learning can interfere with retention, but sleep acts as a kind of adhesive. It binds the memory in place, and the longer you sleep, the more layers are added. Over time, the memory becomes not just something you remember, but something you know. But there's a limit. Not everything that passes through the hippocampus is eligible for long-term storage, and some things are actively suppressed. The brain sometimes encounters conflicting information, two versions of an event or a mistake that contradicts a known rule, and chooses to let one version fade. This is part of the unlearning process. It's not always obvious, but it's essential for flexibility. Memory isn't a perfect archive. It's a constantly evolving model of what matters. Sleep ensures that model is kept up to date. And then there's the question of emotional content. Memories with emotional weight are more likely to be preserved. This is why you tend to remember emotionally charged events more vividly than neutral ones. But sleep doesn't just preserve these memories, it modifies them. As your brain replays emotional content, it often reduces the emotional intensity while keeping the factual core. This serves a purpose. It lets you retain what you need while dampening what could overwhelm you. This filtering applies across the board. Emotion, logic, motor skills, sensory impressions, all of it is sorted, stored, or forgotten. It's a form of internal housekeeping, quiet, automatic, precise. You don't direct this process. You can't force your brain to forget something. But the opposite is true as well. You can't always force it to remember. What you can do is support the conditions under which this process works best. That means sleeping consistently, giving your brain the uninterrupted time it needs, avoiding the substances and stresses that interfere with its rhythms. Because when it has what it needs, your brain handles the rest. It keeps what you need. It lets go of what you don't. It files things where they belong. It reduces confusion. It makes your mind easier to live in. And each morning you wake with a version of your experiences that's slightly more refined than the night before, not just remembered, understood. You've probably felt it before. A solution appears out of nowhere. A phrase you are searching for lands effortlessly in your mind. A strange, imaginative combination of ideas comes to you, not while you're thinking hard, but while you're somewhere softer, somewhere between focus and distraction. Or sometimes in the middle of the night, when you weren't thinking at all. Sleep seems to know how to unlock creativity, not in the way that brainstorming or discussion can, but in a quieter, less deliberate way. When the mind is no longer trying to force connections, sleep finds them anyway, and often, they're the ones you couldn't reach when you were awake. This isn't luck, it isn't magic, it's biology. During sleep, and especially during REM, the brain enters a different mode of operation, one where associative boundaries loosen, sensory inputs fall silent, and neural circuits can reorganize freely. The result is a temporary mental state where ideas are more likely to combine in novel ways. Creativity isn't just about having ideas, it's about making unexpected connections, and that's what the dreaming brain is uniquely positioned to do during REM sleep. The stage most associated with dreaming, the brain's emotional and visual centers become highly active. The amygdala lights up. The occipital cortex, responsible for processing images, comes to life. But the prefrontal cortex, the area involved in logic, self-monitoring and constraint, remains relatively quiet. That combination creates a mental environment where the usual rules are suspended. Without the tight oversight of the waking mind, memories, impressions and concepts can flow more freely. The brain doesn't need to check whether an idea is realistic. It doesn't need to evaluate whether something is useful. It simply explores. And in that exploration, it often stumbles across insight. This process is why dreams can feel surreal. People, places, and events are stitched together in ways that don't conform to waking logic. Time skips. Rules dissolve. Symbols replace specifics. But embedded in that surrealism is something useful. The freedom to associate without judgment. In waking life, your thoughts are largely linear. You start with an idea, follow it to the next, evaluate as you go. That's efficient for problem solving and communication, but it can also limit what you notice. The brain tends to follow the most direct path, the one you've walked before. Sleep changes that. During REM, the path widens. Ideas from separate categories, different memories, different parts of your knowledge base are allowed to touch. Sometimes that creates confusion, but other times it leads to novelty, combinations you wouldn't have made otherwise. Studies have shown that people perform better on creative tasks after REM sleep than after non-REM or wakefulness. When asked to generate unusual uses for an object, find hidden patterns, or solve problems that require lateral thinking, participants who had REM sleep scored higher. It's not just that they were less tired, their minds were more flexible. This flexibility is supported by changes in the brain's neurochemistry. During REM, levels of norepinephrine, a chemical associated with focus and vigilance, are extremely low. This reduction seems to allow for broader, less filtered associations. At the same time, acetylcholine levels remain high, which supports neural activation and learning. The brain is both relaxed and active, a rare combination that fosters creative recombination. There's also evidence that dreams themselves may serve a function in creative thinking. While not every dream is meaningful, and most are forgotten by morning, the act of dreaming may help the brain rehearse, simulate, or restructure experiences. For example, a dream might not show you a literal solution to a problem, but it might present an emotional rehearsal that changes how you approach it the next day. Some researchers believe that dreams are a kind of cognitive sandbox, a space where the brain tests different combinations of thoughts, emotions, and imagined outcomes without the constraints of reality. That doesn't mean every dream is insightful, but it means the dreaming process creates conditions where insight is more likely. Historical examples support this. Many artists, scientists, and inventors have reported that ideas came to them during or after sleep. Mary Shelley famously described the inspiration for Frankenstein as emerging from a dream. Dmitri Mendeleev, the chemist who developed the periodic table, claimed to have seen its structure in his sleep. Paul McCartney said the melody for Yesterday came to him fully formed upon waking. These stories aren't just anecdotes, they're reflections of how the brain works. When you step away from effort, when you let the mind drift, the networks responsible for creativity become more active. Sleep amplifies that effect. But even beyond REM, other stages of sleep contribute to creativity in quieter ways. Deep sleep, though less associated with dreaming, plays a role in memory consolidation. It helps the brain stabilize the raw material, the knowledge, the experiences, the impressions that creative thinking later draws from. Without that foundation, the flexible associations of REM would be less useful, so the process is layered. Deep sleep organizes, REM recombines. Together they provide both the structure and the spontaneity that creative thought requires. And the benefits don't end when you wake up. Even if you don't remember your dreams, the effects of sleep on creativity can still show up during the day. You might notice it when a problem that seemed unsolvable suddenly feels simpler, when a metaphor arises without effort, when a new way of expressing something clicks into place. That's not random. It's the result of neural adjustments that began while you were asleep. This is why people often say, "Let me sleep on it." It's not just a way of stalling. It reflects an intuitive understanding that rest allows the brain to reframe, to see things differently, to sort what matters from what doesn't, to give space for ideas to breathe, and even short naps can show this effect. In experiments, people who took a nap that included REM were better at solving creative word puzzles than those who didn't nap, or who only entered non-REM stages. The key seems to be not just rest, but the right kind of mental state, one that allows for mental flexibility without conscious interference. It's important to understand that creativity doesn't always feel like revelation. Sometimes it feels like fluency, like ideas coming more easily, like being able to follow an impulse without overthinking it, like knowing which direction to go without explaining why. Sleep supports that too. It reduces inhibition in useful ways. It strengthens the connections between relevant ideas and weakens the noise, and over time it helps you build a creative identity, not just through sudden insights, but through the steady refinement of how you think. People who sleep well tend to be more open to new ideas. They're less rigid in their thinking. They're better able to adapt to unfamiliar situations. That's not just about mood or energy. It's about how their brains have been shaped, night after night, by the interplay of structure and exploration. You don't have to do anything special to access this. You don't need to try to dream of a solution. You don't need to force yourself to be imaginative before bed. Just giving your brain the time to cycle through its natural sleep stages is enough. It will do the work for you, quietly, behind the scenes. And in the morning, when the prefrontal cortex comes back online and your thoughts become more organized, you might find that something new has surfaced. A better phrase, a sharper concept, a clearer sense of what you were reaching for, not because you worked harder, but because you gave your brain the chance to connect the dots. Creativity, at its core, is about seeing what's already there in a new way, and sleep, night after night, helps you do exactly that. Not every night is peaceful. Sometimes sleep takes a darker turn. You find yourself in a version of reality that feels a little too sharp, a little too close. Your heart races, your mind reacts. It's only a dream, but the fear is real, and when you wake, it lingers. A sense that something followed you back, something the light can't quite erase. Nightmares are part of the sleep experience, not always frequent, not always remembered, but present enough to be familiar. They're not glitches, they're not failures of the system. In many cases, they're the system doing its work, sorting through fear, preparing for the unpredictable, and occasionally surfacing things you didn't expect to see again. To understand nightmares and what they say about the emotional mind, it helps to look at how sleep handles fear in general. Throughout the day, your brain is scanning for threats. Most of the time, this happens beneath awareness, a glance at someone's expression, the tone of a sentence, a sudden change in atmosphere. Your amygdala, the part of the brain responsible for detecting and responding to danger, is always monitoring. It doesn't just react to immediate threats, it catalogues them, it keeps records, and not all of them are updated or resolved while you're awake. Sleep offers a chance to revisit those records, not to amplify them, but to process them, to find a different way of holding what was difficult. The brain doesn't forget fear automatically. It has to relearn safety, and part of that relearning happens at night. REM sleep plays a central role here. During this stage, the amygdala becomes highly active, more so than during other parts of the sleep cycle. But while this might sound like it would increase fear, what actually happens is more complicated. The brain appears to be reactivating emotional memories in a context that's safer, one where stress hormones are dialed down and physical responses are muted. You're reliving, but without the full physiological consequences. This allows the memory to be reprocessed, not erased, but reshaped. The core event may remain, but its emotional charge can change. Over time, and with repeated sleep cycles, distressing memories become less sharp, not because you've forgotten them, but because they've been folded into the broader emotional archive, surrounded by context, softened by integration. But sometimes, especially when something is unresolved or intense, this reactivation breaks into consciousness. It becomes vivid, it becomes narrative, it becomes a nightmare. Nightmares are dreams with emotional weight, often fear, but sometimes shame, grief, helplessness, or confusion. They're not random. They tend to draw from your own emotional history, though not always in literal ways. A nightmare might not show you the exact thing you fear. It might use symbols, metaphors, shifts in identity or time, but the feeling is clear, and the feeling is real, even though the content isn't. This is part of what makes nightmares so unsettling. Your body reacts, heart rate rises, breathing quickens, muscles may tense. In some cases, especially during REM, you might even partially awaken in the middle of one, with that fear still coursing through you, trying to separate dream from reality. But even when they're difficult, nightmares are not without purpose. In many cases, they reflect the brain's attempt to resolve something, a fear that hasn't found closure, a situation that left a mark, a possibility that your emotional system is still preparing for. The brain doesn't need you to understand the symbolism, it just needs the emotional system to feel it again, this time in a controlled setting where it can begin to shift. There's evidence that people who regularly experience nightmares often have more sensitive emotional systems during the day. Their amygdalas are more reactive, their emotional memories are more vivid, and their brains may be more inclined to replay distressing content in an effort to make sense of it. In some people, this process works. Nightmares become less frequent over time as the underlying emotions are processed. In others, especially those who've experienced trauma, the system gets stuck, The same content replays. The fear doesn't decrease. Sleep becomes associated with dread, and the emotional archive remains inaccessible. This is where nightmares can become pathological, not just disturbing but disruptive. Recurrent nightmares, especially those linked to trauma, can interfere with the brain's ability to process fear effectively. The fear remains fresh, the emotional resolution doesn't occur, and the cycle feeds itself. But even here, science is finding tools. Therapies like imagery rehearsal, where people practice rewriting the content of their nightmares while awake, have been shown to reduce nightmare frequency and intensity. The idea is not to deny the emotion, but to give the brain a different version of the story to replay, something that allows emotional closure without reactivation of panic. Because ultimately, what sleep tries to do, in all its stages, is bring emotional equilibrium. It doesn't avoid fear. It walks through it slowly, carefully, reactivating only what it thinks it can work with. Nightmares are one expression of that process, a visible surface to a deeper emotional reorganization. Children experience more nightmares than adults. Their emotional systems are still developing. Their memories are more impressionable. Their understanding of threat and safety is still forming. As they grow, their brains learn to regulate fear more efficiently. Nightmares often decrease, but some persist, especially in people with high sensitivity or a history of instability. Not all nightmares come from trauma. Some are rooted in everyday stress, deadlines, conflict, uncertainty. The brain doesn't always distinguish between types of pressure. It reacts to what you feel, not just what happened. And sometimes, what you feel at a subconscious level doesn't surface until sleep allows it to. Interestingly, there's a difference between nightmares and bad dreams. Nightmares tend to wake you. Bad dreams can be disturbing, but you sleep through them. Both are part of emotional processing. But nightmares, especially recurrent ones, tend to signal that something unresolved is pressing harder for attention. Dream content studies show recurring themes: being chased, falling, losing control, failing at something important. These aren't just tropes. They reflect universal emotional concerns, vulnerability, insecurity, loss. Each person's version is unique, but the emotions underneath are shared, and they're stored, revisited, sorted, and rebalanced, slowly, across many nights. Your brain keeps an emotional archive, not a scrapbook of every feeling, but a layered system of associations, contexts, and lessons. When something distressing happens, it's stored along with everything else: the sensations, the images, the meaning you gave it at the time. Sleep returns to that archive periodically. It doesn't go shelf by shelf, it doesn't need to, but it knows which entries are still highlighted, which ones are still triggering a signal, and night by night, it works to reduce the volume of that signal, not to silence you, but to make the feeling bearable, integrated, understood. Sometimes that process is invisible. You sleep through it, and you wake a little more stable. Other times the process is visible. It takes the shape of a dream that shakes you awake. But the goal is the same: to update the emotional system, to restore the ability to feel without being overwhelmed, and to help you face the next day, not by pretending the fear wasn't real, but by reminding you that you made it through the night anyway. Most of the time, sleep is a background rhythm. It's there when you need it, quiet, automatic. You don't think much about it until it starts to slip. And when it does, the changes aren't always obvious at first. A little irritability, a small lapse in focus, a conversation you don't remember clearly, you miss a detail, you lose a name. Something feels just slightly off. Then it happens again and again. And slowly you begin to notice. It's not just tiredness. It's a kind of unraveling. Sleep deprivation doesn't tear through the brain all at once. It pulls thread by thread. One system falters, then another. You lose clarity, then precision, then steadiness. Eventually, even your sense of yourself, how you feel, how you relate to others, how you think, begins to drift. This process doesn't require total sleep loss. Even modest reductions in sleep, getting 6 hours instead of 8, 5 hours instead of 7, can start the process. You might not feel exhausted, you might say you're used to it, but the brain is keeping score, and it knows when the deficit begins to accumulate. The first things to go are usually cognitive. Attention becomes less stable, you miss changes in your environment, you react more slowly, your ability to sustain focus drops. Tasks that once required little effort begin to demand more. You reread the same sentence. You forget why you opened a tab. Your brain begins to drift even when you're trying to stay anchored. Then comes memory. The encoding of new information weakens. You might sit through a meeting, a lecture, a conversation, and later realize you retained almost nothing. That's because the hippocampus, which plays a major role in forming new memories, becomes less effective with sleep loss. It's still taking in information, but the signals don't stick. Without sleep, the memories aren't consolidated. They simply dissolve. Mood also begins to shift. The amygdala, the brain's emotional alarm system, becomes more reactive. Studies show that sleep-deprived individuals have up to a 60% increase in emotional reactivity to negative stimuli. At the same time, the prefrontal cortex, the region responsible for regulation, decision-making and impulse control, starts to disconnect. That means the emotional volume goes up, but the ability to manage it goes down. You might feel more anxious, more irritable, more emotionally raw. Things that wouldn't normally bother you start to feel personal. You react faster and more intensely. And when it happens again the next day and the day after, it stops feeling like a reaction. It starts to feel like your new baseline. This is where the unraveling deepens, because the longer you go without proper sleep, the more your internal reference points begin to shift. You start adapting to dysfunction. Your brain adjusts its expectations downward. This is called sleep state misperception, when a sleep-deprived person begins to underestimate how impaired they are. You say you're fine, but cognitively you're not. You think you're focused, but your performance shows otherwise. Reaction time slows, logical reasoning declines, problem-solving suffers, and you don't notice the full extent of it until you try to do something complex. Multitasking, planning, learning something new, and suddenly everything takes longer, feels harder, or falls apart. Physiologically, the body also starts to signal distress. Cortisol, the stress hormone, stays elevated longer. Heart rate variability decreases. Inflammatory markers rise. The immune system becomes less responsive. Over time, this makes the body more vulnerable to illness, less efficient at healing, and more reactive to daily stressors. But sleep deprivation doesn't just affect the body and brain separately, it disrupts their coordination. Hormonal rhythms shift, appetite changes, ghrelin, which stimulates hunger, increases, leptin, which signals satiety, decreases. This is one reason why sleep-deprived people tend to crave more calorie-dense foods, especially sugar and fat. The body starts looking for quick energy, while the mind loses its ability to evaluate long-term consequences. And then there's the social cost. People who are sleep-deprived tend to withdraw. Emotional intelligence decreases, empathy declines. You miss social cues, misinterpret tone, respond with less patience. This can strain relationships, not because you intend it, but because the emotional buffer that sleep provides is no longer there. This isn't just anecdotal. Studies using facial recognition tasks have shown that sleep-deprived individuals are worse at interpreting expressions. They mistake fear for anger, miss subtle signs of discomfort, respond with more negativity. Over time, this affects not only how you perceive others, but how they perceive you. And all the while, the brain continues compensating. It reroutes attention, it pushes harder on tired circuits, It uses more energy to perform the same tasks. This compensation works, for a while, but it comes at a cost. Brain metabolism increases, error rates rise, creativity and flexibility decline. You can still function, but only just. Then there's the effect on perception. When sleep deprivation becomes prolonged, the brain begins to lose its grip on reality. Sensory processing becomes less reliable. Time feels distorted. You may feel detached from your body or surroundings. In extreme cases, people can experience hallucinations, seeing or hearing things that aren't there. These aren't just dreams leaking into wakefulness. They're the brain's desperate attempt to stabilize consciousness when the boundaries have broken down. Even one night of total sleep deprivation can trigger symptoms that resemble psychiatric conditions, anxiety, depression, even temporary psychosis. This doesn't mean that sleep loss causes mental illness, but it does mean that sleep is critical to mental stability. It holds the structure of the mind in place, and when it's removed, the mind begins to fray. Chronic sleep deprivation compounds all of this. Memory loss becomes more pronounced. Concentration becomes harder to recover. The brain's capacity for learning diminishes. Emotional numbness may take over. Motivation declines. Tasks that once felt purposeful begin to feel meaningless. This isn't just fatigue, it's a cognitive and emotional recession. And yet, sleep is often the first thing people sacrifice when life gets busy. Deadlines extend into the night. Stress interferes with rest. Screens push sleep later. Noise and distraction chip away at the early stages of sleep, which are critical for transition. And over time, you begin to normalize it. You treat sleep as optional, something that can be caught up on later. But the effects don't wait. The brain begins its descent almost immediately, and recovery takes longer than most realize. 1 or 2 good nights can help, but they don't erase the cumulative cost, especially when deprivation is chronic. The mind doesn't bounce back like a switch. It needs time. It needs stability. There's no perfect threshold. Some people can manage with slightly less sleep than others, but for most adults, consistent sleep under 6 hours per night leads to measurable declines in function, cognitive, emotional, and physical. And the longer it goes on, the harder it becomes to see the damage because it starts to feel normal. Sleep loss also increases the risk of serious long-term conditions, cardiovascular disease, obesity, diabetes, depression, dementia. Not because sleep is a cure for these things, but because chronic deprivation weakens the systems that normally help regulate and prevent them. The good news is that the brain remains responsive to restoration. Sleep is a healing process, not a binary state. Even after deprivation, the brain knows how to recalibrate. It enters deeper stages more quickly, it prioritizes REM, it clears backlog. The system wants to repair itself. It just needs the chance. And when it gets that chance, the unraveling slows. Then it stops. Then slowly the threads are rewoven. Attention stabilizes. Emotion softens. Memory begins to return. Thought regains clarity. You don't need perfection, just consistency. Enough nights, long enough, undisturbed. This is what sleep does. It preserves the self, quietly, completely. And when it's taken away, even slowly, the self begins to slip. But the brain doesn't forget what wholeness feels like, and every time you sleep, it starts putting the pieces back together. There's a particular kind of tired that doesn't feel like tired. It doesn't come with yawns or heavy eyelids. It doesn't even feel unpleasant at first. It feels more like a haze. You're still awake, still moving, still capable of talking and listening and thinking. But something in the clarity is gone. There's a fog, not thick enough to stop you, just enough to slow you down. Like walking through a room filled with smoke you can't see, but feel. Your thoughts move slower. Your attention doesn't hold. You forget the last sentence you read. You walk into a room and forget why you're there. You answer a question and forget what you just said. This is what the brain begins to feel like without sleep. It doesn't shut down all at once. It doesn't announce its decline. It slips, quietly, system by system. That fog is your frontal lobe losing access to its usual resources, the region responsible for higher order thinking, decision-making, and attention. It's still online, but its bandwidth has narrowed. It's using more energy to do less. It's compensating for something that's no longer working properly. The restorative scaffolding that sleep provides each night. And while that's happening, there's a flicker, a momentary lapse in awareness. You lose track of your surroundings. You forget what you were doing. These aren't just distractions. They're micro-sleeps, brief periods, often lasting just a few seconds when parts of your brain go offline. You might not even notice them. Your eyes stay open, you're still upright. But inside, something has dimmed. Microsleeps are the brain's emergency response. They're not planned, they're not controlled. They happen when deprivation has reached a point where the system can no longer stay fully awake. The brain tries to rest in small pockets, grabbing milliseconds of recovery wherever it can. But these brief rests come at a cost, in focus, in safety, in memory. And while that's happening, there's a fray. The emotional system begins to unravel. What normally feels manageable starts to feel disproportionate. You react too fast or not at all. You misread people's expressions. Your tolerance disappears. Stress feels sharper. Joy feels muted. Irritation lingers. This isn't weakness, it's wiring. Without sleep, the amygdala becomes hyperactive. The prefrontal cortex, which normally keeps it in check, stops regulating efficiently. That means small stresses feel big. Big emotions feel uncontainable. You know you're overreacting, but you can't stop it. You try to calm down, but the internal tools aren't available. You're in a car with no steering, just a gas pedal that's stuck. These aren't rare experiences. They're predictable, repeatable, confirmed in study after study. In one experiment, participants were kept awake for 24 hours, then shown emotionally charged images. Their brain scans revealed much higher activation in the amygdala and much lower connectivity between it and the frontal lobes. This combination, more emotion, less regulation, mirrors what's seen in anxiety and mood disorders. The symptoms become harder to separate. Sleep doesn't just rest the mind, it resets the emotional circuitry. When that reset doesn't happen, the emotional system stays on high alert. And it doesn't take long before that starts to feel normal. Like this is who you are now, not something your brain is temporarily struggling through. You forget that sleep used to help you. Sleep used to make things feel easier to hold. Without it, not only does the present feel heavier, the past and future do too. Memory becomes less reliable. You recall things out of order. Your sense of time starts to bend. A task that took 5 minutes feels like it took an hour. Something from yesterday feels like it happened days ago, or weeks, or not at all. This is because sleep loss disrupts the hippocampus, the brain's indexing system. New memories don't get encoded properly. Old memories become harder to access. You're aware something happened, but you can't place it. You're sure you said something, but no one remembers. You go looking for a file in your mind and the folder is missing. That's not forgetfulness in the ordinary sense. That's the brain losing access to its organizational system. And while this is happening, your sense of motivation begins to erode. The world starts to feel less interesting. Even things you care about feel distant. Not because you've lost interest, but because the systems that support engagement, anticipation and reward are disrupted. Dopamine signaling becomes less stable. The brain's ability to predict and enjoy positive outcomes drops. It doesn't feel like sadness always. Sometimes it just feels like flatness. You find yourself staring at a task, knowing you need to do it, but unable to start. Not because you're lazy, not because you don't want to, but because your brain no longer knows how to shift from stillness into motion. Sleep loss also distorts self-perception. People report feeling detached from their own thoughts, as if watching themselves from the outside. Their own voice feels unfamiliar. Their own reactions feel like someone else's. This is called derealization, a temporary disconnection from identity, often brought on by extreme fatigue. In clinical sleep studies, some participants who went multiple nights without sleep began experiencing hallucinations, brief vivid images, shadows that weren't there, movement in the corner of the eye. These weren't imagined memories, they were sensory distortions, the brain trying to fill in gaps when it could no longer make accurate predictions. This doesn't mean sleep loss causes psychosis in healthy people, but it does mean that the line between reality and imagination becomes thinner without sleep. The mechanisms that keep those lines distinct, the ones that filter, verify, and stabilize your perception, rely on nightly maintenance. Without it, they drift. Even language begins to break down. People who are sleep deprived often use more filler words. They repeat themselves. They lose track of grammar. They forget words mid-sentence. Speech becomes slower, less coherent. This is because the regions responsible for language production, including Broca's area, are especially sensitive to fatigue. The result is not just a slower brain, it's a noisier one. Internal signals become harder to filter. Irrelevant thoughts intrude. You start one task and think of another. You try to listen but find yourself narrating instead. The signal-to-noise ratio drops, and with it, your sense of control. And it's cumulative. The longer the deprivation continues, the more these effects build. Sleep debt doesn't stay isolated, it seeps into memory, into perception, into behavior, into the systems that help you know who you are, what you care about, and how you respond to the world. And yet, from the outside, you may look fine. That's part of the problem. People can stay functional for a long time. They show up, answer emails, hold conversations. But inside, the brain is operating on emergency mode, barely keeping up, spending more energy to stay in the same place. That fog, that flicker, that fray, they're not quirks, they're signs. They're the mind's quiet way of saying, I need sleep. And the sooner it gets it, the sooner the restoration can begin. It doesn't take much for the fog to start lifting. One full night can improve emotional regulation. A few nights in a row can restore attention. Within a week of consistent, high-quality sleep, memory improves, motivation returns, language stabilizes, and perception clears. Sleep is not a reward for being productive. It's the precondition for being whole. And when it returns, so do you. There's a timing to everything your body does, not just in the way your heart beats or your lungs rise and fall, but in the quiet, invisible rhythms that shape when you feel alert, when you feel tired, when you're hungry, when you're cold. These aren't habits, they're clocks, and they're not ticking on your wrist or your wall, they're inside you. Your brain, along with nearly every other system in your body, runs on a rhythm. Not one you consciously set, but one that evolved to anticipate the rising and falling of the sun. This internal timing system is called your circadian rhythm, and it doesn't just tell you when to sleep, it influences how you sleep, how deeply, how consistently, how restoratively. The conductor of this internal orchestra is a small cluster of neurons deep in the brain, just above the place where the optic nerves cross. It's called the suprachiasmatic nucleus, the SCN, and it's located in the hypothalamus. The SCN is sensitive to light, especially blue light. It uses light signals to calibrate the body's clock every day, ensuring that your biological time stays synchronized with the external world. Light enters the eyes, even when they're closed, and signals to the SCN whether it's morning or night. In response, the SCN adjusts the timing of hormone release, body temperature, and sleep-wake cycles. It doesn't do this instantly. The process is gradual, slow, deliberate. The system prefers predictability. Sudden changes, like staying up all night or flying across time zones, throw it off. This is why jet lag feels so strange. Your body is no longer aligned with the time outside. You try to sleep when your brain thinks it should be awake. You wake when your body still believes it's midnight. The circadian rhythm hasn't caught up. It takes a few days, sometimes longer, But it's not just about travel. Even small disruptions to your sleep schedule, going to bed 2 hours later on weekends, or sleeping in too late, can confuse the system. The SCN expects rhythm, consistency, and when that's lost, the effects ripple outward. Melatonin is one of the most well-known players in this rhythm. It's often called the sleep hormone, but it doesn't make you sleep. It tells the body that it's time to prepare for sleep. Melatonin levels start to rise a few hours before your typical bedtime, peaking in the middle of the night, and then falling as morning approaches. The SCN controls this release, regulating when the signal begins and ends. If you look at a screen too close to bedtime, especially one that emits blue light, melatonin production is delayed. The brain reads the light as daytime, even if it's midnight. That pushes sleep later, weakens the depth of rest, and can shift the rhythm forward night after night. But melatonin is just one part of the picture. Cortisol, often associated with stress, is also part of the sleep rhythm. Its levels are lowest around midnight, then begin rising before dawn, helping to wake you gently and prepare your body for the demands of the day. The timing of this cortisol rise is critical. If it happens too early, you wake feeling restless. If it happens too late, you struggle to feel alert in the morning. Temperature plays a role too. Your core body temperature drops slightly in the evening as part of the sleep preparation process. This cooling helps induce drowsiness. It's why a warm bath before bed can actually help you fall asleep. The warm water triggers a drop in core temperature afterward, and it's why sleeping in a room that's too warm can lead to shallow, fragmented sleep. Your brain needs that drop. It expects it. These rhythms extend beyond the brain. Your liver, your heart, your digestive system, all of them have their own local clocks. And while the SCN sets the master schedule, these peripheral clocks rely on other cues too. Food timing, activity, light exposure, all of it contributes to the orchestration. When everything is in sync, your systems work efficiently. When they fall out of rhythm, performance and health decline. Shift workers experience this dissonance more than most. When you sleep during the day and work at night, you're asking your body to do the opposite of what it evolved to do. The brain resists at first. Melatonin stays high when it shouldn't. Alertness drops during the night. The immune system becomes less responsive. Digestion slows. Over time, chronic misalignment with circadian rhythms has been linked to higher risks of metabolic disorders, cardiovascular disease, and mood disturbances. It's not just about when you sleep, but how well your biological clock aligns with your environment and behavior. People often describe themselves as night owls or early birds, and while some of that is habit, much of it is genetic. These natural tendencies are called chronotypes, and they influence when your body feels most alert, when melatonin is released, and when you experience your peak mental and physical performance. Forcing yourself into a rhythm that doesn't match your chronotype can work temporarily, with caffeine, with alarms, with commitment, but it's not always sustainable. The brain prefers to work with its natural timing, not against it. And when you sleep at a time that matches your internal clock, the quality of that sleep is better, deeper, more restorative. Circadian rhythms also influence the structure of sleep itself. Sleep isn't uniform, it cycles through different stages, from light sleep to deep, slow-wave sleep to REM. The timing and balance of these stages shift across the night. You tend to get more deep sleep earlier in the night and more REM later. That's why going to bed too late can reduce your REM sleep, even if you sleep the same number of hours. The circadian clock shapes not only when you sleep, but how that sleep is distributed. It also affects the timing of dreams. Most vivid, emotionally charged dreams occur in the final third of the night during REM-rich periods. If you cut sleep short, you miss those cycles. And because REM is associated with emotional processing and memory consolidation, that loss has consequences. It's not just that you miss dreaming, you miss the brain's chance to do some of its most important overnight work. Your ability to learn is also influenced by circadian timing. Cognitive performance varies across the day. Most people experience a peak in alertness in the mid-morning, a dip in the early afternoon, and a second smaller peak in the early evening. Trying to study or solve complex problems during your natural dips is harder, not because you're less capable, but because the brain is working against its clock. Even mood follows these patterns. Depression and anxiety symptoms often worsen at certain times of day. People with disrupted circadian rhythms, due to insomnia, shift work, or irregular routines, are at higher risk for mood disorders. This isn't just correlation. There's growing evidence that stable circadian rhythms help regulate the neurotransmitters responsible for mood stability, and recovery is rhythm-based too. Muscle repair, hormone regulation, immune activity, all of it ebbs and flows in time with your internal clock. Athletes who sleep in sync with their rhythms recover faster. People recovering from illness heal more efficiently when sleep is prioritized and well-timed. So when you think of sleep as one action, falling into bed, closing your eyes, you miss the larger structure. It's not one action. It's the final act of an entire system operating in coordination. The body prepares long before you lie down. Hormones shift. Body temperature drops. Alertness fades. Neural activity begins to wind down. The entire system is moving towards sleep, slowly, steadily, predictably, if you let it. Modern life pushes against this. Artificial light, screens, noise, irregular schedules, shifted meal times. The brain doesn't resist because it's fragile. It resists because it's wired for a world with rhythm. Without one, it does its best, but it loses its sharpness, its balance, its memory of when things are supposed to happen. Restoring that rhythm doesn't require perfection, just awareness, a consistent sleep schedule, dimmer lights in the evening, less screen time before bed, light in the morning, meals at regular times, small signals that tell the SCN, this is morning, this is night, this is rest. And as those signals stabilize, so does everything else. Sleep becomes easier, moods even out, focus returns, memory strengthens. The brain doesn't just sleep, it plays in time, like an orchestra returning to tempo. Sleep is never quite the same twice. Even within your own life it changes, slowly, steadily. The amount, the rhythm, the texture, what you need, how deeply you rest, how long it takes to fall asleep, what your dreams feel like, what you remember in the morning, all of it shifts. From the beginning, sleep is there, but not in the form you know it now. Infants are born sleeping in fragments. Their days are broken into pieces, short cycles of waking and sleeping that repeat over 24 hours. There's no internal clock that distinguishes night from day yet. The circadian rhythm hasn't taken shape. Instead, sleep is driven by basic needs: feeding, warmth, comfort. It comes and goes in waves. A newborn might sleep 16 hours a day or more, but not all at once. Sleep is light, frequent, and often incomplete. REM sleep dominates, making up nearly half of a newborn's sleep time. This is likely because the brain is growing at an extraordinary rate. Neurons are forming connections, shaping sensory maps, building the architecture that will later support memory, language, and thought. REM sleep, with its intense brain activity and rapid eye movements, appears to support that early development. Slow-wave sleep, the deeper, more restorative kind, is also present, but less pronounced in the earliest months. As the child grows, the pattern begins to change. Around 3 to 6 months, circadian rhythms begin to form. The brain starts responding more consistently to light and dark. Melatonin production begins to follow a rhythm. Night becomes sleep time, day becomes wake time. By the time a child reaches a year old, sleep begins to consolidate into longer blocks. Naps still happen, 1 or 2 during the day, but nighttime sleep stretches out. Total sleep time may still exceed 12 hours, but the brain is learning to sustain sleep more efficiently. REM decreases slightly. Deep sleep becomes more structured. The foundation for adult-like sleep is starting to take shape. During early childhood, sleep remains long and essential. Between ages 2 and 5, children often sleep 11 to 13 hours a day. Naps may continue, though they gradually taper off. Brain development during this period is still rapid. Language acquisition, emotional regulation, motor control. Sleep supports all of it. Without enough of it, children show more behavioural issues, less attention, and slower cognitive development. Interestingly, during this time, children spend more time in deep, slow-wave sleep than at any other point in life. Their brains enter these restorative stages with ease and stay there longer. This is when growth hormone is released, when immune function is reinforced, when the body and brain repair themselves at full strength. But as children move into adolescence, something changes again, not just in the structure of sleep, but in its timing. The adolescent brain begins to shift its circadian rhythm forward. Melatonin is released later in the evening. The natural time to fall asleep drifts later. At the same time, early school schedules remain fixed. Teenagers end up going to bed late and waking up early, losing hours of sleep each week. And because REM sleep dominates in the later part of the night, that's what gets cut. This mismatch between biological rhythm and social schedule creates a kind of chronic jet lag. Many adolescents live in a state of partial sleep deprivation, not always severe, but consistent. The effects show up in mood, attention, learning, memory, even physical health. It's not laziness or rebellion. It's biology asking for time the world doesn't always give. In terms of structure, teenage sleep begins to resemble adult sleep more closely. The sleep cycles, around 90 minutes each, alternate between non-REM and REM. Deep sleep still occurs early in the night. REM dominates the later hours, but the need for sleep remains higher than it does in adulthood. Most teenagers still need 8 to 10 hours a night. Few get it. By early adulthood, sleep becomes more individualized. Chronotypes become more stable. Some people naturally feel more alert in the morning, others in the evening. Total sleep need averages around 7 to 9 hours, but varies by genetics, health, stress, and lifestyle. The brain is no longer developing at the pace it once was, but sleep still supports learning, memory consolidation, emotional regulation, and physical recovery. This is often the stage when sleep is most neglected. Work schedules, social obligations, screens, stress. All of it competes with rest. Sleep becomes something to sacrifice, something to postpone, and yet even short-term deprivation has noticeable effects. Reaction times slow, memory falters, emotional balance wobbles. Sleep doesn't stop being essential just because life gets louder. In the 30s and 40s, the structure of sleep begins to shift again, subtly at first. Deep, slow-wave sleep becomes less dominant. It doesn't disappear, but it shrinks. Some people notice more frequent awakenings, especially in the second half of the night. It takes longer to fall back asleep. Sleep feels lighter, and the effects of missed sleep become harder to ignore. Sleep latency, the time it takes to fall asleep, may increase slightly. REM sleep remains important, but deep sleep becomes harder to enter. This is partly due to changes in the brain's ability to generate the large, slow oscillations characteristic of slow-wave sleep. These changes are normal, but they do make the brain more sensitive to disruptions. Noise, light, stress, caffeine. Hormonal rhythms also shift during midlife. In women, perimenopause and menopause bring changes in estrogen and progesterone levels, which affect sleep quality and thermoregulation. Hot flashes, night sweats, and mood fluctuations can make sleep more fragmented. In men, gradual decreases in testosterone may also influence sleep patterns, though the effects are generally milder. During this phase of life, sleep disorders become more common. Insomnia, sleep apnea, restless leg syndrome, all increase in prevalence. Some of these are physiological, others are tied to stress, responsibility, or health conditions, but the result is the same. Sleep begins to feel less predictable, and without intervention, the brain adapts by lowering expectations. It accepts shorter or lighter sleep as normal, but the body still pays the price. In older adulthood, 60s, 70s and beyond, the architecture of sleep changes more noticeably. Total sleep time often decreases. People tend to go to bed earlier and wake earlier, a shift sometimes referred to as advanced sleep phase. Sleep becomes more fragmented. Awakenings are more frequent. The proportion of deep sleep continues to decline. REM sleep may also become shorter and less intense. But these changes don't mean older adults need dramatically less sleep. They still benefit from 7 to 8 hours a night. The challenge is in getting it. Medical conditions, medications, reduced activity, and changes in circadian signaling can all interfere. The result is often lighter sleep, more time in bed without sleep, and more daytime napping. Daytime naps in small doses can be helpful, but if they become too long or too late, they can make nighttime sleep harder to sustain. The cycle becomes self-reinforcing. You sleep less at night, so you nap more during the day. Then you're less tired at night, and the pattern continues. Managing this balance becomes part of healthy aging. Sleep also plays a role in cognitive aging. Studies have found links between poor sleep and increased risk of cognitive decline, including Alzheimer's disease. One proposed mechanism involves the glymphatic system, the brain's waste clearance system, which becomes more active during deep sleep. When deep sleep decreases, the clearance of metabolic waste, including beta amyloid, may slow down. This doesn't mean poor sleep causes dementia, but it suggests that long-term sleep quality matters, not just for how you feel now, but for how your brain functions in the decades to come. Despite these changes, sleep remains flexible. It can improve with small adjustments, consistent timing, reduce caffeine, increase daylight exposure, reduce screen time, mindfulness practices, and, when needed, medical support. Even in later life, sleep can be stabilized. It may look different than it did at 20, but it can still be restorative, still deeply beneficial, and across all stages of life, one thing stays the same. The brain doesn't stop needing sleep. It adapts, it adjusts, but it never forgets how to rest. From infancy's cycles to childhood's deep waves, from adolescence's late nights to adulthood's busy compromises, from midlife's shifting rhythms to the light, early mornings of old age, sleep is not static, it grows with you. The brain doesn't go quiet when you sleep. It doesn't power down, it doesn't turn off. In some ways, it becomes more active, not louder but busier, not chaotic but coordinated. While the body rests, the brain begins its own kind of work. Not random, not background noise, but organized communication. Region speaking to region. Neurons sending patterns across networks. A conversation of sorts, one you don't hear, one you never consciously join, but one that shapes how you remember, how you feel, and how you understand yourself. These conversations aren't held in words, they're made of pulses, oscillations, waves, the language of voltage and timing, electrical whispers between billions of cells, short bursts that carry fragments of a day, echoes of thoughts you had, scenes you lived through, emotions you barely processed. And this is when the brain sorts through it all. The process begins soon after sleep starts. As you enter non-REM sleep, particularly the deeper stages, a specific pattern of brainwaves begins to appear. Slow, high-amplitude oscillations known as delta waves take over. These waves move like tides, rising and falling about once per second. During this phase, the thalamus, a relay center for sensory input, quiets down. It stops passing external signals to the cortex. In this isolation, the brain starts focusing inward. Within this quiet frame, sleep spindles emerge. These are short bursts of faster brainwave activity, lasting less than 2 seconds. They occur mostly in stage 2 sleep, and they represent another form of internal communication. Spindles are believed to help in memory consolidation, protecting new memories from interference and strengthening them through rehearsal. Then there are sharp wave ripples. These occur in the hippocampus, a region critical for memory. These fast, high-frequency events appear during deep sleep and are associated with the reactivation of specific memories. When you learn something during the day, the hippocampus holds on to it. During sleep, it plays it back, quietly, rapidly, and sends copies of the memory to the cortex for long-term storage. What you're left with in the morning is the result of that replay, not a raw copy of the experience, but a distilled version. The essence, what was worth keeping, what connects to what came before. The hippocampus and the cortex discuss, in a language of firing patterns, what should stay and what should go. This isn't something you decide, it's something the brain decides for you. It's not just memory being processed. Emotional experiences go through similar replays. During REM sleep, when the cortex becomes active again and vivid dreams occur, emotional memories are revisited with reduced levels of norepinephrine, a neurotransmitter involved in arousal and stress. This chemical context allows the brain to re-experience emotional events with less physiological reactivity. The goal isn't to forget them, but to detach them from their sharpest edges, to integrate them more calmly into the larger narrative of your life. Different brain regions have roles in this. The amygdala, which tags emotionally significant events, becomes active during REM. So does the anterior cingulate cortex, which helps process emotional conflict. The medial prefrontal cortex, which normally regulates emotional responses during the day, is relatively quiet, allowing more unfiltered content to surface. These shifts let the brain run its simulations, uncorrected by logic, rich in emotional complexity. That's part of why dreams can feel so charged, so personal, so strange. The content isn't rational, but it is meaningful, to the brain, if not to the conscious mind. These are not random images. They're constructed from memories, fragments, ideas, and fears that were activated recently or emotionally. It's the brain pulling on threads, testing them, trying them in different configurations, and it doesn't do this blindly. Research using brain imaging has shown that the hippocampus, the visual cortex, the motor cortex, the language centers, all show selective activation during different kinds of dreams. The brain is not broadcasting noise, it's rehearsing, reconfiguring, learning, it's speaking to itself. Outside of REM, communication happens more quietly. During deep non-REM sleep, connectivity between different cortical regions strengthens. This is when information gets consolidated into existing networks, not just stored, but linked. When a new piece of knowledge finds its place among everything else you know. This integration is what turns isolated facts into usable insight. It's what makes learning durable. The conversation doesn't stay local, it moves. Signals bounce from hippocampus to prefrontal cortex, from sensory areas to associative networks, from emotion centers to decision-making regions. Timing matters. The rhythms of sleep, slow oscillations, spindles, ripples, coordinate when these messages are sent and received. Like instruments in an orchestra, each part of the brain takes its turn. If these rhythms are disrupted, by noise, by light, by waking, the conversation becomes disjointed, messages are lost, integration fails. And the next day, you may notice, you forgot something you just learned. You feel more reactive, you struggle to connect ideas. The brain didn't finish its work. Sleep is not passive, it's not idle, it's not downtime, it's the brain's working shift. But instead of responding to the outside world, it's tuning the inside one. It's checking what fits, what's stable, what's out of place. It's clearing out redundancies, tagging important patterns, discarding noise. You wake with less than you had, but it's better organized, better understood. These nightly conversations also influence your sense of identity. Memory doesn't just store facts. It builds the narrative you call yourself. Every night your brain reinforces certain connections, weakens others. It's deciding what defines you, what matters, what doesn't, who you are. Not in a philosophical sense, but in a neurological one. You don't remember most of your dreams. You don't need to. The conscious recall isn't required for the brain's nightly operations to have meaning. The work happens below awareness. Just as you don't remember every heartbeat or every breath you took while sleeping, you don't remember the neural discussions, but their impact accumulates. Some scientists believe this process may extend to insight, to the kind of problem solving that happens indirectly. You go to bed stuck on something, and in the morning the solution feels closer. Not handed to you, but more accessible. The brain wasn't idle while you slept. It was sifting through possibilities, mapping connections, and something changed. Not because you thought harder, but because you rested. In animal studies, researchers have recorded neurons firing in patterns during sleep that mirror activity during prior waking tasks. A rat that ran a maze during the day would replay that path at night, sometimes even faster, as if compressing time. This replay isn't just about memory, it's rehearsal. The brain is learning while it sleeps. Humans show similar replay activity, though it's more complex. Tasks involving motor learning, visual recognition, even emotional interpretation all show improvement after sleep, and brain activity during the night reflects rehearsal of those skills. The communication between regions strengthens, the patterns become more refined. Even creativity may depend on these conversations. When unrelated ideas come together in a new way, it's often the result of neural reorganization during sleep. Not chaotic, but structured. Not guessed, but tested. Quietly, in the dark, between parts of the brain that don't often speak during the day. This is why fragmented sleep can feel so disorienting. It's not just that you're tired, it's that the conversation was interrupted. The process was paused. The brain didn't finish syncing its parts, and until it does, things feel off. There's still more to learn. The full picture of what the brain does while we sleep is still unfolding. But what's clear is that sleep is a time of deep internal coordination. The kind of coordination that builds memory, stabilizes emotion, restores clarity, and reinforces identity. Every night your brain talks to itself, not randomly, but with purpose, quietly, carefully, like a team going over the day's work, like an editor refining a story, like a system reviewing its logs, updating its map, preparing for another day. And you wake with the result, not aware of the process, but shaped by it. Sleep is not just a nightly event, it's a form of regulation, a system your brain uses to stay balanced, not only for memory or energy or learning, but for something more fragile, something more difficult to quantify: mood, resilience, emotional stability, the ability to face your life and feel, somehow, that it's manageable. It would be simpler if sleep and mental health were two separate systems, if one could be measured without the other, but they aren't separate, they're tightly wound, each one affecting the other in ways that can be subtle, circular, and hard to untangle. A night of poor sleep doesn't just leave you tired, it leaves you more sensitive, more easily overwhelmed, less able to regulate your thoughts or contain your emotional reactions. You notice it in small ways. A comment that stings more than it should, a decision that feels heavier than it is, a worry that won't quiet down. These are not isolated effects. They are reflections of what's happening under the surface. When sleep is disturbed, even slightly, the brain's ability to manage emotion changes. The amygdala, your internal alarm system, becomes more reactive. It sends stronger signals, faster. The prefrontal cortex, the part that helps you pause, reflect, and regulate, becomes less responsive. It doesn't suppress the signal. It doesn't weigh the options. It just lets the reaction happen. This shift is not temporary. If sleep loss continues, the pattern becomes more ingrained. The emotional system operates without breaks. Minor frustrations feel major. Thoughts spiral more easily, optimism fades, it becomes harder to imagine that things will get better, and that's just the beginning. Over time, chronic sleep problems are linked to a higher risk of developing mental health conditions, including depression, anxiety disorders, bipolar disorder, and even psychosis. These links are not just associations, they reflect mechanisms, shared pathways, disrupted rhythms that affect mood, perception, and behavior. In depression, for example, sleep disruption is one of the most common symptoms. Some people struggle to fall asleep, others wake too early, some sleep excessively, but without rest. The architecture of sleep changes. REM arrives earlier, it lasts longer. The normal structure, with deep sleep early in the night and REM later, collapses. These shifts don't just reflect depression, they contribute to it. The brain isn't getting the right kind of rest, emotional processing is incomplete, memories are not properly integrated, the next day feels heavier, and the cycle continues. Anxiety disorders show a different pattern. People with anxiety often experience hyperarousal at night, racing thoughts, physiological tension, restlessness. The nervous system stays on alert, even in the absence of real danger. Sleep onset becomes difficult. The mind won't quiet down, and even when sleep occurs, it's shallow, fragmented. The brain never fully lets go. This leads to a paradox. The more anxious you are, the harder it is to sleep. The less you sleep, the more anxious you feel. The system reinforces itself, and each day that passes without resolution, the baseline shifts. What once felt like mild discomfort becomes chronic tension. Bipolar disorder presents another layer. In manic or hypomanic states, sleep often disappears almost entirely. People feel energetic, focused, even euphoric, and they don't feel tired. But this lack of sleep fuels the episode. The brain becomes overstimulated, judgment declines, reality becomes distorted. And when the crash comes, sleep returns, sometimes excessively, in the depressive phase. Disrupted sleep patterns in bipolar disorder are not just symptoms, they are predictors, early signs. In some cases, a change in sleep can precede a shift in mood. That's why tracking sleep in bipolar patients is critical. It's not just about rest, it's about forecasting the weather inside the mind. Even in schizophrenia, one of the most severe psychiatric conditions, sleep shows distinct abnormalities. People with schizophrenia often have disrupted circadian rhythms, fragmented sleep, and reduced slow-wave sleep. These changes are not just side effects of medication, they're present even before diagnosis. The relationship between sleep and psychosis is still being studied, but the patterns are clear. When sleep is unstable, so is perception. The overlap between sleep and mental health is so consistent that some researchers are beginning to treat sleep directly, not as a secondary symptom, but as a target in its own right. In many cases, improving sleep leads to improvements in mood, focus, and emotional regulation. Cognitive behavioral therapy for insomnia, CBTI, is one example. It focuses on sleep hygiene, thought patterns, and behavioral routines, and in clinical trials it has shown not only to improve sleep quality, but to reduce symptoms of depression and anxiety, sometimes even more effectively than medication. This doesn't mean sleep fixes everything, but it means that sleep can open a door. It can soften the sharpest edges, create space for other interventions to work, restore the energy needed to engage with life again. The brain depends on rhythm, regularity, predictability. Sleep provides that, or at least it can when given the chance. But mental illness often disrupts those rhythms. It shifts bedtimes, disturbs circadian signals, alters melatonin release, changes light exposure. All of these elements feed back into sleep, which then feeds back into mood. That's the uneasy dance, each system trying to regulate the other but falling out of step. Social rhythm therapy is one approach that tries to re-establish that balance. It focuses on stabilizing daily routines, not just sleep, but meals, activity, and social interaction. The goal is to give the brain what it craves: structure. When structure returns, sleep improves, and when sleep improves, the brain becomes more capable of managing itself. Neurotransmitters also play a role. Serotonin, dopamine, norepinephrine, all are involved in mood, and all are regulated in part by sleep. During REM, serotonin activity decreases. During deep sleep, dopamine is rebalanced. The brain uses these stages to tune the chemical environment. When sleep is fragmented, these tuning processes fail. The result is emotional instability, not from one missing chemical, but from the failure of the orchestra to stay in sync. Inflammation is another piece of the puzzle. Chronic sleep deprivation increases levels of inflammatory markers, and inflammation has been linked to depression, fatigue, and cognitive impairment. The connection may be indirect, but the result is real. A tired brain is more inflamed. A more inflamed brain is more reactive, and a more reactive brain is more vulnerable to distress. Trauma adds further complexity. People who have experienced trauma often have disrupted sleep. Nightmares, insomnia, fragmented REM. The brain remains on alert, even in the absence of present danger, and sleep, which should be a time of healing, becomes a time of reactivation. This is why trauma-focused therapies often include sleep work, because until the brain can rest, it cannot reprocess what it's been through. The good news is that the system remains flexible. Even after months or years of poor sleep, it can be re-regulated, slowly, gently, with consistency. The brain responds to cues: light, temperature, timing, routine. When those cues are clear and repeated, the brain begins to trust them. Sleep returns, not always immediately, not always fully, but it returns, and with it, stability. Not perfection, not immunity from stress, but enough regulation to feel capable again, enough clarity to see the next step, enough energy to try. That's what sleep does. It doesn't eliminate pain, it doesn't fix complex lives, but it gives the brain what it needs to try again, which is often the first and most important thing. Every night, without announcement, your brain begins a ritual. It doesn't need reminders. It doesn't need to be convinced. It knows the pattern, the sequence, the steps. This ritual isn't cultural or conscious or decorative. It's biological, fundamental, the oldest habit your body has. Sleep isn't something the brain waits for. It's something the brain builds, piece by piece, signal by signal. Long before you close your eyes, the process begins. Light fades, melatonin rises, temperature drops, attention narrows. The world recedes by fractions. Thought slows, intention dims, and quietly, the ritual takes hold. There's no ceremony, just a shift, from outer to inner, from active to receptive, from stimulus to stillness. You don't notice the threshold, that's part of how it works. Sleep doesn't require you to make it happen. It only requires that you let it. When you do, everything follows. The brain changes its rhythm. Electrical activity transforms. Chemicals redistribute. Whole regions go offline, while others come alive. You're not unconscious. You're altered. Existing in a different state, governed by different rules. In this state, maintenance begins. Not mechanical, not manual. More like orchestration. Coordinated, precise, and deeply necessary. Memory gets sorted, unused pathways get pruned, emotional heat is released, systems reset, and as all this happens, you're somewhere else entirely. Not aware of the work, but held inside it. Even dreaming, which seems so disconnected from real life, is part of the ritual. A byproduct of integration, a side effect of rearrangement. The brain pulls images and symbols and narratives from your experience, not to entertain you, but to test how things fit. What matters, what repeats, what can be let go. This ritual repeats every night with variation. Some nights are quiet, some vivid, some filled with images, others blank. But the work happens either way. Whether you remember it or not, whether it feels satisfying or strange, your brain is participating, and it will keep doing so for as long as you let it. The structure is ancient. The rhythm was set long before you had language for it, before you were born, before your ancestors had electricity, long before artificial light or screens or alarms, back when the only signal was the setting of the sun and the cooling of the air. The brain still prefers that world, one where night means dark, where wind down is gradual, where cues are steady. It can adapt to modern rhythms, but it does so reluctantly. Too much light, too much noise, too many interruptions, and the ritual frays. It still occurs, but incompletely. You wake more often, you remember less, you feel unrested, and when the ritual is disrupted long enough, it stops feeling automatic. Sleep becomes something you chase, something you bargain with, something you resent. But it was never meant to be a struggle. Sleep is not a test of willpower. It's a biological return. The return isn't just to rest, it's to balance, to clarity, to continuity. Every system in the brain uses sleep. Every function, memory, emotion, cognition, perception, performs better because of it. Without it, the system doesn't collapse immediately, it adapts. But the adaptations come at a cost, and that cost is cumulative. Each night missed pulls the system slightly out of sync. Each recovery night restores it, but only partially. That's why consistency matters more than volume. The brain isn't trying to catch up on hours, it's trying to re-establish rhythm. This rhythm is fragile, easily pushed, easily forgotten, but never fully erased. Even after weeks or months of irregular sleep, the ritual can return. The brain never forgets the steps. It only needs the signal, darkness, quiet, stillness, time. With those, it begins again. You may not feel it immediately. The return is slow, fragmented at first. Sleep deepens gradually. Dreams grow longer. Waking becomes smoother. Thoughts clearer. Mood steadier. The ritual rebuilds itself one night at a time, and with each repetition, the effects compound. It's not a transformation, it's a reversion. Back to how the brain prefers to operate, not in exhaustion, not in survival mode, but in alignment, with itself, with the world around it. The ritual supports more than just health, it supports identity. When you sleep, the brain reinforces your sense of who you are, the memories it keeps, the emotions it files, the patterns it favours. They're not random, they're you, edited down, shaped, smoothed, stabilised. Without sleep, the narrative becomes unstable. You remember less, feel more reactive, lose the thread, but with sleep, the self returns. Recognisable, intact, even slightly improved. That's why, even when life is chaotic, even when time feels stretched thin, sleep remains one of the most protective things you can offer your brain. Not because it fixes everything, but because it prepares you to face everything again. Night after night, the ritual gives you back to yourself, without demand, without judgment, without failure, just the quiet repetition of a pattern your brain already knows, a return to balance, a recalibration of everything inside. And as it unfolds, you don't need to watch it. You don't need to track or measure or understand every part. You just need to allow it, to make space for the system to do what it's always done. Because this ritual isn't optional, it isn't decoration, it isn't indulgence, it's the architecture of being human. A process that happens whether you notice it or not. A restoration that begins the moment you let go, and continues long after you forget the moment you drifted. If you'd like to drift a little longer, you're welcome to stay. Your brain knows what to do. Sleep well. If you've made it this far, thank you for letting this be part of your night. Whether you're still awake or already half dreaming, your brain has been listening. Quietly, softly, maybe even beginning its work. If this brought you any sense of calm or helped you ease into rest, you can always find your way back here. And if you'd like to support this space for more science, more sleep, and more gentle wandering through how the brain works, feel free to like, subscribe, or share this with someone who could use a softer night. Until next time, take care, be kind to your brain, and rest well. Good night.